Subscribe to the channel so you don't miss out on any of these videos. Imagine a giant cosmic puzzle, a mystery that stretches across millions of light years, wrapped in blazing colors and shimmering light. These are the kiloparsec rings, massive structures in distant galaxies that seem to defy our understanding of how stars are born and evolve. Think about this for a second. These rings aren't just decorative patterns in the night sky. They're bustling hubs of activity, places where stars are being forged at an unimaginable rate, almost as if the universe decided to create entire neighborhoods of suns all at once. But why? What triggers this intense star formation in such perfectly circular regions? And what secrets are they hiding from us? This isn't just a question for scientists. It's a question that strikes at the core of what we know about the universe. These rings challenge our understanding of galaxies, dark matter, and even the forces that hold the cosmos together. They open doors to a universe we barely comprehend, one that constantly surprises us with its creativity and complexity. And if that doesn't hook your curiosity, think about this. Somewhere in those rings, there could be planets forming around those newborn stars. Planets with their own stories, their own mysteries. Maybe even life. Kiloparsec rings are more than just structures. They're phenomena that demand explanation. Each one of these rings spans thousands of light years across, with their diameters measured in kiloparsecs, a single kiloparsec being about 3,260 light years. These colossal features are found in a variety of galaxies, from spirals to ellipticals, and their sheer size and brightness make them stand out like cosmic beacons. But their beauty is only part of the story. To truly appreciate the enigma of kiloparsec rings, we need to dive deep into the forces that create them, the processes that sustain them, and the mysteries that still linger despite decades of observation and study. Let's start with what makes these rings so fascinating: their intense star formation. When you look at a kiloparsec ring, you're essentially looking at a star-making factory operating on a galactic scale. These rings are often teeming with bright, young stars that have just formed from dense clouds of gas and dust. This isn't a slow, gradual process. It's a dramatic, high-energy event. The stars in these rings are born in bursts, almost as if a galactic engine is revving up to maximum output for a limited time. But why does this happen in a ring shape? This is where the mystery deepens. One prevailing theory involves the gravitational interactions between galaxies. When two galaxies pass close to each other, or even collide, their mutual gravity can create immense tidal forces. These forces can compress gas and dust into specific regions, often along the edges of the galaxy, where they form a ring. Another possibility is that these rings are created by bar structures within galaxies. In this scenario, the gravitational influence of the bar funnels gas toward the center of the galaxy while simultaneously ejecting some of it outward, creating a ring-like pattern. And then there's the idea of resonances. Just like a musical instrument can resonate at certain frequencies, galaxies can experience resonances due to the gravitational influence of nearby objects or internal structures. These resonances can concentrate gas and dust in specific regions, leading to the formation of rings. The Milky Way, our own galaxy, has a bar structure at its core and possibly even a faint ring of star formation, though not as dramatic as the kiloparsec rings seen in other galaxies. But even if we understand how these rings form, there's still the question of their longevity. How long can such a structure last before it dissipates or evolves into something else? Observations suggest that kiloparsec rings are relatively short-lived on cosmic timescales, perhaps lasting a few 100 million years. This might seem like a long time to us, but in the life of a galaxy, it's just a fleeting moment. During this time, however, these rings can produce a significant fraction of the stars in their host galaxies, shaping their future in profound ways. What's even more intriguing is the role of dark matter in these phenomena. Dark matter, the mysterious substance that makes up most of the universe's mass, plays a crucial role in shaping galaxies. While we can't see dark matter directly, its gravitational effects can influence the formation and evolution of kiloparsec rings. Some researchers speculate that the distribution of dark matter in a galaxy can create the conditions necessary for these rings to form, acting as an invisible scaffolding that guides the movement of gas and stars. And let's not forget about the role of supermassive black holes. Many galaxies with kiloparsec rings also have active galactic nuclei powered by supermassive black holes. The energy released by these black holes can heat the surrounding gas, potentially influencing the formation of rings. In some cases, the black hole's activity might even trigger star formation by compressing gas into dense clumps. It's a delicate balance of forces, gravity, pressure, and energy, all working together to create these stunning structures. The study of kiloparsec rings is far from over. In fact, it's just beginning. New telescopes and technologies are allowing us to study these rings in greater detail than ever before. Observatories like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, are giving us unprecedented views of the gas, dust, and stars within these rings. These observations are helping scientists test their theories and refine their models, but they're also raising new questions. For example, why do some galaxies have kiloparsec rings while others don't? What determines the size and intensity of these rings? And what happens to them over time? One thing is certain: kiloparsec rings are a testament to the universe's ability to surprise us. They remind us that the cosmos is not a static, unchanging place but a dynamic, evolving system full of wonders waiting to be discovered. They challenge our understanding of the laws of physics and push us to think beyond what we know. And perhaps most importantly, they inspire us to keep looking up, to keep asking questions, and to keep exploring the mysteries of the universe. Understanding kiloparsec rings isn't just about deciphering how they form and function, it's about unveiling their profound implications for galactic evolution. These massive, star-forming rings act as cosmic laboratories, offering a rare glimpse into processes that govern not just their host galaxies, but the universe as a whole. To grasp their significance fully, we must explore the intricate interactions of the elements within these rings, the forces at play, and the cosmic ripple effects they create. One of the most striking aspects of kiloparsec rings is their composition. They're not merely collections of stars but rather a rich tapestry woven from gas, dust, and energetic particles. The interplay between these elements sets the stage for a cosmic symphony of star formation. At the heart of this process lies molecular hydrogen, the raw material for stars. Dense clouds of this gas collapse under their own gravity, igniting nuclear fusion and giving birth to new stars. The sheer abundance of molecular hydrogen in kiloparsec rings is staggering, often concentrated at levels far exceeding those found in the rest of the galaxy. This overabundance raises another question: where does all this gas come from? Some theories suggest that the gas is funneled into the ring by interactions with other galaxies, a phenomenon known as galactic accretion. When galaxies interact or collide, their gravitational forces can strip gas from one galaxy and deposit it into another, often along ring-like structures. Alternatively, internal mechanisms, such as the movement of material along spiral arms or the influence of galactic bars, can concentrate gas into rings. Whatever the source, the result is the same: a fertile environment where stars can form at an accelerated rate. But kiloparsec rings aren't static entities. They're dynamic, ever-changing systems influenced by feedback mechanisms from the very stars they create. Massive stars, for example, emit intense ultraviolet radiation and stellar winds that can compress nearby gas, triggering further star formation. At the same time, these forces can also disrupt the ring's delicate balance, dispersing gas and halting the star-forming process in certain regions. Supernova explosions add another layer of complexity. When these massive stars reach the end of their lives, they explode, sending shockwaves through the surrounding gas. These shockwaves can either compress the gas, sparking new waves of star formation, or blow it outward, effectively quenching the ring's activity. The balance between these opposing forces, star formation and feedback, is a critical factor in the life cycle of kiloparsec rings. It's a cosmic tug-of-war that determines not only the lifespan of the ring but also its impact on the host galaxy. For instance, the energy released by supernovae and young stars can heat the gas in the ring, creating outflows that extend far beyond the galactic plane. These outflows can enrich the surrounding intergalactic medium with heavy elements, a process known as galactic recycling. Over time, this enrichment can influence the formation of new stars and even entire galaxies, making kiloparsec rings key players in the broader cosmic ecosystem. The role of kiloparsec rings in galactic evolution becomes even more intriguing when we consider their connection to central supermassive black holes. Many galaxies with prominent kiloparsec rings also harbor active galactic nuclei, AGN, powered by these black holes. The relationship between the rings and the AGN is a subject of ongoing research. Some scientists speculate that the inflow of gas toward the galaxy's center, which contributes to the formation of the ring, also feeds the black hole, fueling its activity. Conversely, the AGN's energy output can influence the ring by heating the gas and altering the conditions for star formation. This intricate interplay between kiloparsec rings and supermassive black holes highlights the interconnected nature of the universe. These rings aren't isolated phenomena. They're deeply embedded in the fabric of their host galaxies, influencing and being influenced by the structures around them. Even dark matter, the elusive substance that makes up most of the universe's mass, plays a role. Simulations suggest that the distribution of dark matter in a galaxy can shape its gravitational potential, creating the conditions necessary for kiloparsec rings to form and persist. While we can't observe dark matter directly, its fingerprints are evident in the behavior of these rings, offering yet another clue to its mysterious nature. As we delve deeper into the study of kiloparsec rings, we're confronted with new questions that challenge our understanding of the cosmos. For example, why do some galaxies develop kiloparsec rings while others don't? Is it purely a matter of chance, dictated by the galaxy's interactions and internal dynamics, or are there underlying factors we've yet to uncover? What role do these rings play in the overall life cycle of galaxies, and how do they contribute to the formation of large-scale cosmic structures like galaxy clusters and superclusters? These questions aren't just academic, they're a call to action for the next generation of astronomers and astrophysicists. With the advent of new technologies and observatories, we're on the brink of a golden age of discovery. Instruments like the James Webb Space Telescope, JWST, and the Atacama Large Millimeter/Submillimeter Array, ALMA, are already revolutionizing our understanding of kiloparsec rings. These tools allow us to peer deeper into the universe than ever before, capturing detailed images and spectra of these rings and the galaxies that host them. With each new observation, we're piecing together the puzzle of kiloparsec rings, uncovering their origins, evolution, and ultimate fate. But the study of kiloparsec rings isn't just about answering scientific questions. It's about something deeper, our insatiable curiosity and our quest to understand our place in the universe. These rings remind us of the beauty and complexity of the cosmos, of the countless mysteries waiting to be discovered. They're a testament to the power of human imagination and ingenuity, proof that even in the face of the unknown, we can find meaning and wonder. And perhaps that's the greatest mystery of all, the way the universe, in all its vastness and complexity, can inspire awe and curiosity in beings as small and fragile as us. Kiloparsec rings are more than just astronomical phenomena. They're symbols of our ongoing journey to explore, to learn, and to dream. The journey into understanding kiloparsec rings doesn't just provide insights into galactic structures. It also opens doors to understanding the broader principles that govern the universe. These massive star-forming regions act like cosmic time capsules, preserving clues about the processes that shaped galaxies billions of years ago. When we examine these rings, we are effectively looking into the past, glimpsing the universe as it was in its more formative stages. This perspective helps us decode not only the life cycles of galaxies, but also the mechanisms that shape the very fabric of the cosmos. One intriguing aspect of kiloparsec rings is their role in galaxy classification and evolution. Galaxies with such rings often belong to a specific category known as ring galaxies. These structures can arise from direct collisions between galaxies or gravitational interactions that leave behind symmetrical, ring-like patterns. In some cases, the rings are tightly concentrated near the galactic center, forming what scientists call nuclear rings. In others, they are more spread out, creating structures that resemble vast ripples in a cosmic pond. Regardless of their size or placement, these rings are often sites of heightened star formation, earning them the nickname starburst rings. Starburst activity in kiloparsec rings is so intense that it can significantly affect the surrounding environment. As young, Hot stars emit enormous amounts of ultraviolet radiation. They ionize the nearby hydrogen gas, causing it to glow brightly in the ultraviolet and optical wavelengths. This luminous emission makes kiloparsec rings some of the most visually striking features in the universe, often standing out even in distant galaxies. This is particularly important for astronomers studying galaxies at high redshifts, where such rings can serve as signposts for identifying areas of intense activity in otherwise faint and distant galaxies. But the story of kiloparsec rings isn't just about light and energy, it's also about balance. The rate of star formation in these regions is governed by a delicate interplay of forces. On one hand, gravitational collapse drives the accumulation of gas, enabling star formation. On the other hand, feedback processes, like stellar winds and supernova explosions, push back against this collapse. This balance is further complicated by the inflow of material from other parts of the galaxy. For instance, spiral arms can act as conveyors, channeling gas toward the central regions and feeding the ring. Similarly, galactic bars, elongated structures that stretch across some galaxies, can exert gravitational forces that funnel gas inward, enriching the ring and sustaining its star-forming activity. The interplay between these forces creates a dynamic, ever-evolving environment. In some cases, the ring grows more massive over time, accumulating material and producing stars at an accelerating rate. In others, feedback processes dominate, dispersing the gas and effectively quenching star formation. This tug-of-war determines the lifespan of the ring, which can range from a few million to several hundred million years. Understanding these life cycles is critical for unraveling the larger puzzle of galaxy evolution, as the processes occurring in kiloparsec rings often mirror those happening on a galactic scale. A particularly fascinating question in the study of kiloparsec rings is their connection to the central supermassive black hole of their host galaxies. Observations reveal that galaxies with active kiloparsec rings often exhibit heightened levels of activity in their central regions, where the black hole resides. This raises the possibility of a causal relationship between the two phenomena. Some researchers hypothesize that the inflow of gas into the ring may eventually reach the black hole, triggering episodes of intense accretion and powering the galaxy's active nucleus. Conversely, the energy released by the black hole, through jets, winds, or radiation, could influence the ring, either by compressing gas to trigger further star formation or by heating and dispersing it, thereby suppressing activity. These interactions highlight the interconnected nature of galactic structures, where seemingly separate components, rings, bars, black holes, and spiral arms, work together in a cosmic dance. They also underscore the role of kiloparsec rings as engines of galactic activity, capable of driving both the formation of stars and the growth of central black holes. This dual role makes them invaluable for understanding the feedback processes that regulate galaxy evolution on both small and large scales. But there's more to kiloparsec rings than meets the eye. Recent studies have revealed that these structures are not just confined to the visible spectrum, but also emit strongly in other wavelengths, such as infrared, radio, and X-rays. Infrared observations, for example, have been particularly valuable for studying the dust within these rings. Dust grains, heated by the intense radiation from young stars, emit strongly in the infrared, allowing astronomers to map the distribution of this material with remarkable precision. This, in turn, provides critical insights into the physical conditions within the ring, such as its temperature, density, and composition. Similarly, radio observations have shed light on the magnetic fields that permeate kiloparsec rings. These fields, though invisible to the naked eye, play a crucial role in shaping the behavior of charged particles within the ring. They can influence the motion of gas, regulate the formation of stars, and even affect the propagation of cosmic rays. By studying these magnetic fields, scientists gain a deeper understanding of the complex interplay between matter and energy in these star-forming regions. X-ray observations, on the other hand, have revealed the presence of hot gas and high-energy phenomena within kiloparsec rings. This is particularly true in galaxies with active nuclei, where the central black hole can emit powerful X-rays that illuminate the surrounding structures. These high-energy observations not only provide a glimpse into the extreme conditions near the black hole, but also help identify regions of star formation and supernova activity within the ring. As we continue to probe kiloparsec rings across multiple wavelengths, we're uncovering layers of complexity that were previously hidden. These observations are transforming our understanding of these structures, revealing them to be dynamic, multifaceted systems that are deeply interconnected with the broader universe. They remind us that even the most familiar objects in the cosmos can hold surprises, challenging our assumptions and pushing the boundaries of what we know. Kiloparsec rings are more than just a fascinating phenomenon. They're a testament to the beauty and complexity of the universe. They offer a window into the processes that drive the formation and evolution of galaxies, shedding light on some of the most fundamental questions in astronomy. And as we continue to study them, they serve as a powerful reminder of our own place in the cosmos, a small but curious species, gazing at the stars and seeking to understand the mysteries that lie beyond. The mysteries of kiloparsec rings deepen when we consider their variability and unique characteristics across different galaxies. Not all kiloparsec rings are created equal, and the diversity among them reflects the complex and dynamic environments in which they form. Some are tightly confined to the core of their galaxies, creating bright, concentrated regions of star formation known as nuclear rings. Others extend further outward, resembling broad, diffuse halos that encircle the galaxy's center. This diversity is not just a matter of size or shape, it tells a story about the unique history and evolution of each galaxy. Nuclear kiloparsec rings are among the most striking examples of these phenomena. Found in the central regions of galaxies, these rings are often nestled close to supermassive black holes, forming a dramatic contrast between creation and destruction. In these environments, the gravitational pull from the black hole, coupled with the intense pressure and density of the surrounding gas, creates a perfect storm for star formation. However, the proximity to the black hole also introduces challenges, as the powerful radiation and outflows from the nucleus can either stimulate or suppress star formation depending on the balance of forces at play. In contrast, outer kiloparsec rings are typically found further from the galactic core. These structures often result from interactions between galaxies, where tidal forces distort the shape of one or both participants, creating ripples that propagate outward. These ripples can compress gas in the outer regions, triggering the formation of a ring. In some cases, these outer rings are so vast that they span tens of thousands of light years, encompassing entire star systems and making them visible even in distant galaxies. A fascinating question arises when comparing nuclear and outer rings. Why do some galaxies develop one type of ring while others form the other? The answer lies in the unique dynamics and histories of these galaxies. For instance, the presence of a galactic bar, a long, elongated structure of stars and gas that stretches across the center of a galaxy, can significantly influence the formation of nuclear rings. Bars act as gravitational funnels, channeling gas inward and concentrating it near the center, where it forms a dense ring. Outer rings, on the other hand, are more often associated with galactic mergers or close encounters, where gravitational interactions create the conditions needed for their formation. The formation of kiloparsec rings is not just a question of gravitational dynamics, it's also a matter of timing. Galaxies are not static entities. They evolve over billions of years, undergoing periods of intense activity followed by relative quiescence. Rings may form during particularly active phases, only to dissipate or fade as conditions change. For example, a nuclear ring may form when a galactic bar channels gas inward, but if the bar weakens or disappears over time, the supply of gas may dry up, causing the ring to fade. Similarly, an outer ring may arise from a galactic collision but gradually dissipate as the ripples from the interaction settle. These temporal dynamics make kiloparsec rings valuable tools for studying the life cycles of galaxies. By observing rings at different stages of their development, astronomers can reconstruct the sequence of events that led to their formation and evolution. This, in turn, provides insights into the broader processes that shape galaxies, from the inflow and outflow of gas to the feedback effects of star formation and black hole activity. One of the most exciting developments in the study of kiloparsec rings is the use of advanced telescopes and imaging technologies to observe them in unprecedented detail. Instruments like the Hubble Space Telescope, the ATACM, a large millimeter/submillimeter array, ALMA, and the James Webb Space Telescope, JWST, have revolutionized our ability to study these structures. These telescopes allow astronomers to observe kiloparsec rings across a wide range of wavelengths, from the optical and ultraviolet light emitted by young stars to the infrared radiation from dust and the radio waves from molecular gas. These observations have revealed a wealth of information about the physical properties of kiloparsec rings. For instance, studies using ALMA have mapped the distribution of molecular gas within these rings, showing that it often forms dense clumps or filaments where star formation is most active. Similarly, infrared observations with the JWST have uncovered the presence of complex organic molecules in these regions, suggesting that the building blocks of life may be more common in the universe than previously thought. Perhaps one of the most intriguing discoveries is the role of dark matter in shaping kiloparsec rings. Although dark matter is invisible and interacts with ordinary matter only through gravity, its presence can influence the dynamics of galaxies in profound ways. Simulations suggest that the distribution of dark matter within a galaxy can affect the formation and evolution of rings, particularly in the outer regions. By studying these interactions, astronomers hope to gain new insights into the nature of dark matter and its role in the universe. The study of kiloparsec rings also has implications for understanding the conditions necessary for the formation of planets and, potentially, life. The intense star formation in these regions produces large amounts of dust and heavy elements, which are the raw materials for building planets. By examining the composition and distribution of this material, scientists can estimate the likelihood of planet formation in different parts of a galaxy. This, in turn, helps refine our understanding of where habitable planets might be found, both within our own galaxy and beyond. As we continue to explore the mysteries of kiloparsec rings, we are reminded of the interconnectedness of all things in the universe. These structures, formed by the interplay of gravity, gas, and stars, are not just isolated phenomena. They are part of a larger cosmic tapestry that includes galaxies, clusters, and even the vast web of dark matter that binds the universe together. By studying them, we are not only learning about the specific conditions that give rise to star formation but also uncovering the universal principles that govern the cosmos. The journey into understanding kiloparsec rings is far from over. With each new observation, we uncover new layers of complexity and wonder, challenging our assumptions and expanding our horizons. These cosmic rings, so simple in appearance yet so intricate in structure, are a testament to the beauty and mystery of the universe. A reminder that even in the vastness of space, there are stories waiting to be told, mysteries waiting to be solved, and questions waiting to be asked. The exploration of kiloparsec rings also leads us to broader questions about the role of environment in shaping galaxies and their components. Galaxies do not exist in isolation. They are part of larger structures like groups, clusters, and superclusters, where interactions with neighboring galaxies and the intergalactic medium can significantly influence their evolution. Kiloparsec rings provide a unique window into these environmental effects, as their formation and behavior often reflect the larger cosmic neighborhood. For instance, in galaxy clusters, where hundreds or even thousands of galaxies are gravitationally bound together, interactions between galaxies are frequent and often violent. These interactions can strip gas from galaxies, compress it, or funnel it toward the center, all of which can trigger or suppress the formation of kiloparsec rings. Observations of rings in cluster environments have revealed peculiar properties, such as asymmetries or irregularities that suggest they are being shaped by external forces. These findings highlight the importance of considering the larger context when studying individual galaxies and their features. Another intriguing aspect of kiloparsec rings is their potential connection to galactic winds, powerful outflows of gas driven by intense star formation or the activity of supermassive black holes. Galactic winds can carry vast amounts of material out of a galaxy, sometimes at speeds of hundreds or thousands of kilometers per second. In some cases, these winds may interact with the surrounding gas, compressing it and creating the conditions for ring formation. This feedback loop, where star formation both drives and is influenced by galactic winds, adds another layer of complexity to our understanding of kiloparsec rings. These feedback processes are not just important for the galaxies themselves. They also have implications for the broader cosmic ecosystem. Galactic winds can enrich the intergalactic medium with heavy elements, altering its composition and potentially influencing the formation of new galaxies. By studying kiloparsec rings and their associated phenomena, we can gain insights into these larger-scale processes and their role in shaping the universe. One of the most exciting frontiers in the study of kiloparsec rings is the search for analogs in other cosmic structures. While most research has focused on rings within galaxies, there are hints that similar processes may occur on even larger scales. For example, some simulations suggest that gas flows within galaxy clusters can form ring-like structures, albeit on much larger scales and with different underlying mechanisms. These megaparsec rings, if they exist, would represent a fascinating extension of the principles governing kiloparsec rings, linking the microcosm of individual galaxies to the macrocosm of the universe. The study of kiloparsec rings also intersects with the search for dark matter. While dark matter is notoriously difficult to detect directly, its gravitational effects are readily apparent in the motions of stars and gas within galaxies. By studying the dynamics of kiloparsec rings, astronomers can infer the distribution of dark matter in the regions where these rings form. This, in turn, provides crucial constraints on theoretical models of dark matter and its role in cosmic evolution. For instance, the rotation curves of galaxies, graphs that show how the speed of stars and gas changes with distance from the center, often exhibit peculiar features in the vicinity of kiloparsec rings. These anomalies can sometimes be explained by the presence of dark matter, suggesting that kiloparsec rings may serve as natural laboratories for studying this elusive substance. By comparing observations of rings in different galaxies, researchers can test competing theories of dark matter and refine their understanding of its properties. The connection between kiloparsec rings and dark matter also raises intriguing questions about the role of cosmic filaments, the vast, thread-like structures that make up the large-scale cosmic web. These filaments are thought to be composed primarily of dark matter, with galaxies forming at their intersections. Some researchers speculate that the alignment of galaxies within filaments could influence the formation and orientation of kiloparsec rings, adding yet another layer of complexity to this already intricate phenomenon. As we delve deeper into the mysteries of kiloparsec rings, we are continually reminded of the importance of collaboration and innovation in scientific research. The study of these structures relies on a wide range of observational and theoretical tools, from advanced telescopes and computer simulations to interdisciplinary collaborations that bring together experts in astrophysics, chemistry, and data science. This holistic approach is essential for unraveling the many threads of this cosmic tapestry and piecing together the story of kiloparsec rings. The future of kiloparsec ring research is bright, with new technologies and missions promising to shed even more light on these enigmatic structures. The James Webb Space Telescope, for example, is expected to provide unprecedented views of kiloparsec rings in the infrared, revealing details about their composition and structure that were previously inaccessible. Meanwhile, upcoming surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide a wealth of data on kiloparsec rings across the universe, enabling statistical studies that were previously impossible. These advancements are not just about collecting more data, they are about transforming our understanding of the universe. By studying kiloparsec rings in greater detail and across a wider range of environments, we can refine our theories, challenge our assumptions, and uncover new connections between seemingly disparate phenomena. These rings, so simple in appearance yet so rich in complexity, are a testament to the power of curiosity and the endless possibilities of scientific discovery. Kiloparsec rings are more than just cosmic curiosities. They are windows into the fundamental processes that shape our universe. They remind us that even in the vastness of space, there are patterns and structures that connect us to the cosmos, weaving a story that spans from the smallest particles to the largest galaxies. By studying them, we not only learn about the universe but also about ourselves and our place within this grand and mysterious tapestry. Kiloparsec rings, as mesmerizing as they are, also serve as a reminder of how interconnected the processes in the universe truly are. These rings are not isolated phenomena. They are deeply tied to the very fabric of galactic evolution, star formation, and cosmic interaction. Every kiloparsec ring represents a snapshot in time, a frozen frame of the dynamic forces that continuously shape the cosmos. To understand them fully, we must delve into the intricacies of their formation, their evolution, and their eventual fate. One of the enduring mysteries about kiloparsec rings is the variability in their lifespans. Some rings appear to be transient, existing for just a few million years before dissipating or transforming, while others seem remarkably stable, enduring for hundreds of millions of years. This discrepancy raises questions about the conditions required to sustain a ring and the factors that lead to its demise. Is it the internal dynamics of the galaxy, such as the availability of gas and the behavior of stellar feedback? Or is it external influences like interactions with neighboring galaxies or the intergalactic medium? The answer likely involves a combination of both. Observations of kiloparsec rings in galaxies that have recently undergone mergers suggest that such interactions can create conditions conducive to ring formation. The gravitational forces at play during a merger can cause gas to flow inward or outward, depending on the dynamics of the encounter. In some cases, this can lead to the creation of a dense, rotating ring of gas and stars. However, if the interaction is too violent, or if the galaxy loses too much gas, the ring may not survive for long. On the other hand, stable kiloparsec rings are often found in more isolated galaxies, where the absence of disruptive external forces allows the ring to persist. In these cases, the internal balance of forces within the galaxy, gravity, pressure, and feedback, seems to play a crucial role in maintaining the ring's structure. Understanding this balance is a key goal of current research, as it could reveal fundamental insights into the interplay between star formation, galactic dynamics, and the interstellar medium. Another fascinating aspect of kiloparsec rings is their role in galactic evolution. While they are often viewed as features of individual galaxies, their formation and behavior can have far-reaching implications for the overall development of a galaxy. For example, the intense star formation within a ring can lead to the creation of massive star clusters and even globular clusters, which may survive long after the ring itself has disappeared. These clusters can then contribute to the structural and chemical evolution of the galaxy, enriching it with heavy elements and influencing its long-term dynamics. The interaction between kiloparsec rings and supermassive black holes is another area of active investigation. Many galaxies with kiloparsec rings also host active galactic nuclei, AGN, where matter falling into a supermassive black hole generates enormous amounts of energy. The relationship between the ring and the AGN is complex and likely bidirectional. On one hand, the inflow of gas toward the center of the galaxy, which may contribute to ring formation, can also feed the black hole and fuel AGN activity. On the other hand, the energy released by the AGN can affect the ring, either by triggering star formation through compression of the gas or by disrupting the ring through powerful outflows. These interactions highlight the importance of studying kiloparsec rings not just as isolated structures but as integral components of a galaxy's ecosystem. They also underscore the need for multi-wavelength observations, as different parts of the electromagnetic spectrum reveal different aspects of these complex systems. For instance, optical and ultraviolet observations are crucial for studying young stars and recent star formation, while infrared data can reveal the distribution of dust and older stars. Radio observations, on the other hand, provide insights into the gas dynamics and the presence of molecular clouds, which are the raw material for star formation. Theoretical models and simulations play an equally important role in advancing our understanding of kiloparsec rings. By creating virtual galaxies and subjecting them to various conditions, researchers can test hypotheses about the formation and evolution of rings. These simulations have provided valuable insights into the effects of different parameters, such as the gas density, the strength of feedback mechanisms, and the influence of external forces. They have also highlighted the importance of resolving small-scale processes, such as the behavior of individual star-forming regions, in capturing the full complexity of kiloparsec rings. As we continue to study kiloparsec rings, we are likely to uncover new surprises and challenges. Already, observations have revealed a remarkable diversity in the properties of these rings, from their sizes and shapes to their star formation rates and chemical compositions. This diversity suggests that kiloparsec rings are not a monolithic phenomenon but rather a family of structures that arise under a wide range of conditions. Understanding this diversity is a key step toward unraveling the broader mysteries of galaxy formation and evolution. Moreover, the study of kiloparsec rings has implications beyond astrophysics. The processes that govern the formation and behavior of these rings are deeply rooted in fundamental physics, from the dynamics of gravitational interactions to the thermodynamics of interstellar gas. By studying kiloparsec rings, we can test our theories of these processes under extreme conditions, providing valuable insights that could inform other areas of science. The future of kiloparsec ring research is bright, with new technologies and missions promising to revolutionize our understanding of these fascinating structures. The next generation of telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will provide unprecedented resolution and sensitivity, allowing us to study kiloparsec rings in exquisite detail. These instruments will enable us to probe the physical and chemical conditions within the rings, trace their dynamics, and explore their connections to the larger cosmic environment. At the same time, advancements in computational techniques and artificial intelligence are opening up new possibilities for analyzing the vast amounts of data generated by these observations. Machine learning algorithms, for example, can help identify patterns and correlations that might otherwise go unnoticed, shedding light on the underlying mechanisms that drive kiloparsec ring formation and evolution. By combining these tools with the wealth of data from current and upcoming surveys, researchers are poised to make significant breakthroughs in our understanding of kiloparsec rings and their role in the universe. The mysteries surrounding kiloparsec rings extend far beyond their observable properties, delving into theoretical realms that challenge our understanding of the cosmos. One of the biggest questions involves the origins of these massive structures. While some rings are clearly the result of external interactions, such as galactic collisions or mergers, others seem to arise from purely internal processes. For example, certain galaxies exhibit kiloparsec rings without any signs of recent interactions, suggesting that internal dynamics, such as the effects of bar-like structures or spiral arms, may also play a role in their formation. Another tantalizing mystery involves the relationship between kiloparsec rings and galactic bars. Many galaxies with rings also possess a central bar structure, a linear feature of stars and gas that rotates within the galaxy. These bars can channel gas inward toward the center of the galaxy, potentially triggering the formation of a ring. However, the exact mechanism by which this happens is still not fully understood. Does the bar act as a kind of cosmic pump, funneling gas into specific regions where it can condense and form stars? Or is the relationship more complex, involving feedback loops between the bar, the gas, and the stars within the ring? The chemical composition of kiloparsec rings also offers intriguing clues about their origins and evolution. Observations have shown that these rings often contain high levels of heavy elements, or metals, which are produced by previous generations of stars. This suggests that the gas in these rings is not pristine but has been enriched by earlier episodes of star formation. However, the degree of enrichment can vary significantly from one ring to another, raising questions about the history of gas inflow and outflow in these galaxies. How much of the gas in a kiloparsec ring comes from the galaxy's own reservoir, and how much is acquired from external sources? To answer these questions, astronomers are turning to a combination of observational and theoretical approaches. High-resolution spectroscopy, for example, can provide detailed information about the chemical composition and motion of the gas within a ring, helping to trace its origins and evolution. At the same time, computer simulations are being used to model the behavior of gas in galaxies under different conditions, offering insights into the processes that lead to ring formation. These simulations are becoming increasingly sophisticated, incorporating factors such as magnetic fields, cosmic rays, and the effects of dark matter, which can all influence the behavior of gas on galactic scales. The role of dark matter in the formation and stability of kiloparsec rings is another area of active investigation. Dark matter is believed to make up the majority of a galaxy's mass, yet it interacts with ordinary matter only through gravity. This makes it difficult to study directly, but its effects can be inferred from the motion of stars and gas. In the case of kiloparsec rings, dark matter may play a crucial role in shaping the gravitational potential of a galaxy, influencing the distribution and motion of gas. Understanding this relationship could provide valuable insights into the nature of dark matter itself, as well as its role in galactic dynamics. Another fascinating aspect of kiloparsec rings is their potential connection to cosmic filaments, the vast, web-like structures that make up the large-scale structure of the universe. Galaxies are not distributed randomly throughout space but are instead arranged along these filaments, with clusters of galaxies forming at their intersections. It is possible that the gas flows along these filaments also contribute to the formation of kiloparsec rings, either by supplying fresh material or by triggering star formation through compression. If true, this would link kiloparsec rings to the largest structures in the universe, highlighting their significance as a bridge between local and cosmic scales. As we continue to study kiloparsec rings, new questions are likely to arise, challenging our understanding of these enigmatic structures. For example, what happens to a kiloparsec ring as a galaxy evolves? Does it eventually dissipate, or does it transform into something else, such as a disk of stars or a series of star clusters? What role do these rings play in the life cycle of a galaxy, and how do they influence its long-term development? Answering these questions will require a concerted effort, combining observations across multiple wavelengths, advanced simulations, and innovative analytical techniques. The study of kiloparsec rings is not just about understanding a specific type of structure, it is about probing the fundamental processes that shape the universe. These rings are laboratories for studying star formation, galactic dynamics, and the interplay between ordinary and dark matter. They are also windows into the past, providing clues about the history of the galaxies that host them. By studying kiloparsec rings, we are not only learning about the structures themselves but also gaining a deeper understanding of the cosmos as a whole. In the coming years, the field of kiloparsec ring research is poised to enter a new era, driven by advancements in technology and methodology. New telescopes and instruments will allow us to observe these structures with unprecedented clarity, revealing details that were previously hidden. At the same time, developments in computational power and algorithms will enable more detailed and realistic simulations, providing new insights into the processes that drive ring formation and evolution. By combining these tools, researchers will be able to tackle some of the most pressing questions about kiloparsec rings, unlocking the secrets of these cosmic marvels. The next frontier in the study of kiloparsec rings involves the powerful synergy of observational technology and theoretical modeling. For instance, upcoming facilities like the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, are poised to transform our understanding of these enigmatic structures. JWST's infrared capabilities allow it to peer through dust clouds, capturing the detailed processes of star formation within kiloparsec rings, even in galaxies billions of light-years away. Similarly, SKA's unprecedented sensitivity to radio emissions will help trace the distribution of neutral hydrogen gas, the raw material for star formation, across these rings. Moreover, advancements in machine learning and artificial intelligence are beginning to play a crucial role in analyzing the vast datasets produced by these observatories. By identifying patterns and anomalies in the distribution of stars, gas, and dark matter within kiloparsec rings, AI-driven models can uncover subtle relationships that were previously overlooked. This will enable astronomers to refine their theories about how these rings form and evolve, providing a clearer picture of the underlying physics. One of the most exciting prospects involves using kiloparsec rings as natural laboratories for testing the fundamental laws of physics. For instance, the distribution of gas and stars within these rings can provide constraints on alternative theories of gravity, such as modified Newtonian dynamics, MOND. By comparing observational data with predictions from these theories, researchers can test their validity on galactic scales, potentially shedding light on the nature of dark matter and dark energy. Another intriguing avenue of research involves the connection between kiloparsec rings and active galactic nuclei, AGN, the bright, energetic cores of some galaxies powered by supermassive black holes. In some cases, kiloparsec rings are observed in galaxies with active nuclei, raising questions about the relationship between the two. Does the inflow of gas toward the central black hole trigger the formation of a ring? Or do the energetic outflows from the AGN influence the distribution of gas in the galaxy, shaping the ring? Understanding this interplay could provide new insights into the role of supermassive black holes in galactic evolution. The role of feedback processes in kiloparsec rings is another area ripe for exploration. Star formation within these rings is often accompanied by powerful feedback mechanisms, such as stellar winds, supernova explosions, and radiation pressure. These processes can heat and disperse the surrounding gas, potentially halting further star formation. However, feedback can also compress gas in certain regions, triggering new episodes of star formation. This delicate balance between positive and negative feedback is a key factor in determining the long-term stability and evolution of kiloparsec rings. At the same time, researchers are investigating the role of magnetic fields in shaping kiloparsec rings. Observations have shown that magnetic fields are often aligned with the spiral arms and rings of galaxies, influencing the motion of gas and the formation of stars. By mapping the magnetic fields within kiloparsec rings, astronomers can gain new insights into how these fields interact with other forces, such as gravity and turbulence, to shape the structure and dynamics of the rings. Kiloparsec rings also have implications for our understanding of cosmic star formation rates. These rings often represent regions of intense star formation, contributing significantly to the overall luminosity and chemical enrichment of their host galaxies. By studying the star formation rates within kiloparsec rings, astronomers can refine their models of galaxy evolution, providing a more accurate picture of how galaxies grow and change over time. Beyond their scientific significance, kiloparsec rings capture the imagination because of their sheer beauty and scale. These massive, glowing structures, often spanning tens of thousands of light years, are a testament to the complexity and grandeur of the universe. They remind us that even in the vast emptiness of space, processes of creation and transformation are constantly at work, shaping the cosmos in ways that are both intricate and awe-inspiring. As our understanding of kiloparsec rings deepens, so too does our appreciation for the interconnectedness of the universe. These rings are not isolated phenomena but are instead part of a larger cosmic web, influenced by everything from the behavior of individual stars to the distribution of dark matter on the largest scales. By studying them, we are not only uncovering the secrets of specific structures but are also gaining a deeper understanding of the universe as a whole. The study of kiloparsec rings is a reminder of the power of curiosity and the importance of looking beyond the obvious. These structures, once dismissed as mere curiosities, have proven to be rich sources of insight into some of the most fundamental questions about the universe. They challenge us to think bigger, to ask new questions, and to push the boundaries of what we know. And as we continue to explore these cosmic rings of star formation, we can be sure that they will continue to surprise and inspire us in ways we can scarcely imagine. The enigma of kiloparsec rings continues to fuel some of the most innovative and far-reaching research in modern astronomy. As we delve deeper into their mysteries, the questions surrounding their origins, evolution, and influence grow even more compelling. Theories are evolving, observations are becoming more detailed, and new tools are providing unprecedented insights into these cosmic marvels. A significant area of ongoing investigation is the interplay between kiloparsec rings and the larger galactic environment in which they are embedded. For instance, the orientation and dynamics of a ring are often influenced by the gravitational interactions with neighboring galaxies. In galaxies that are part of groups or clusters, tidal forces from nearby galaxies can distort the shape of the host galaxy, funneling gas into specific regions and potentially triggering the formation of a ring. This raises intriguing questions about how kiloparsec rings function as a kind of cosmic fingerprint, recording the history of a galaxy's interactions with its surroundings. Another intriguing puzzle lies in the temporal evolution of these rings. Observational data suggests that kiloparsec rings are not static structures. They evolve over time. In some cases, rings may form, expand, and dissipate, while in others, they might persist for billions of years. Understanding the factors that govern this longevity is critical. For example, the amount of gas available for star formation, the intensity of feedback mechanisms, and the presence of stabilizing forces such as magnetic fields or dark matter can all influence the lifespan of a ring. A related question involves the fate of the stars formed within these rings. Over time, as stars age and die, they contribute to the chemical enrichment of their surroundings, injecting heavy elements into the interstellar medium. This process, known as chemical recycling, can have a profound impact on the subsequent generations of stars. By studying the metallicity gradients within kiloparsec rings, astronomers can trace the history of star formation and chemical evolution, providing valuable insights into the life cycle of galaxies. The discovery of kiloparsec rings in distant galaxies, billions of light-years away, adds another layer of complexity to the puzzle. These rings provide a window into the early universe, allowing astronomers to study the conditions under which galaxies formed and evolved. For example, observations with the ATACMS, a large millimeter/submillimeter array, ALMA, have revealed kiloparsec-scale rings in galaxies at high redshifts, where the cosmic environment was markedly different from that of the present day. These early rings are often associated with intense bursts of star formation, known as starbursts, which can outshine entire galaxies. The presence of kiloparsec rings in such distant galaxies raises profound questions about their universality and significance. Are these rings a common feature of galaxies throughout cosmic history, or are they unique to specific epochs or environments? If they are universal, what does this tell us about the fundamental processes that govern galaxy formation and evolution? And if they are not, what distinguishes the galaxies that host them from those that do not? Answering these questions requires not only better observations but also more sophisticated theoretical models. For example, hydrodynamic simulations of galaxy evolution, which incorporate the effects of gravity, gas dynamics, and feedback from stars and black holes, are becoming increasingly important. These simulations can recreate the conditions under which kiloparsec rings form, providing a virtual laboratory for testing different hypotheses. By comparing the results of these simulations with observational data, astronomers can refine their theories and gain a deeper understanding of the underlying physics. One of the most exciting developments in this field is the growing ability to study the three-dimensional structure of kiloparsec rings. Traditional observations often provide only a two-dimensional projection of these structures, making it difficult to determine their true shape and orientation. However, advances in techniques such as integral field spectroscopy are changing this. By capturing spectra from multiple regions within a ring, astronomers can map the motion of gas and stars in 3 dimensions, revealing details about the ring's dynamics and geometry. This ability to study kiloparsec rings in 3 dimensions has also opened up new avenues for exploring their connection to other galactic features. For example, in some galaxies, kiloparsec rings are linked to large-scale spiral arms, which act as conduits for gas and stars. In others, the rings appear to be associated with central bulges or bars, which can influence their structure and evolution. By studying these connections, astronomers can better understand how kiloparsec rings fit into the larger picture of galactic anatomy. Another frontier in kiloparsec ring research involves the study of their interaction with black holes. Many galaxies with kiloparsec rings also host supermassive black holes at their centers, which can influence the dynamics of the surrounding gas. In some cases, the accretion of gas onto a black hole can drive powerful outflows, creating shock waves that propagate through the ring and trigger star formation. In others, the black hole's activity may suppress star formation by heating or expelling the surrounding gas. Understanding this interplay between kiloparsec rings and black holes is crucial for understanding the broader processes of galaxy evolution. As we continue to explore the mysteries of kiloparsec rings, one thing is clear: these structures are far more than just curiosities. They are fundamental components of the universe, offering insights into some of the most profound questions in astronomy. They challenge us to think big, to look beyond the obvious, and to consider the interconnectedness of all things. And as we unlock their secrets, we come one step closer to understanding the universe itself, a cosmos of infinite wonder, complexity, and beauty. As we continue to explore the complex and fascinating world of kiloparsec rings, the implications of these structures stretch far beyond simple observations of star formation. They represent a critical piece of the cosmic puzzle, helping us understand the broader mechanics of galaxy evolution, the distribution of matter, and even the fundamental laws of physics that govern the universe. An exciting aspect of studying kiloparsec rings is the potential for discovering new types of galactic structures that challenge existing theories. For example, recent observations suggest that some galaxies might host multiple rings or other complex structures that we have not yet fully understood. These discoveries underscore the importance of continuing to explore new galaxies and refine our models of how these cosmic phenomena develop over time. The role of kiloparsec rings in the formation of galaxies could also provide a more detailed understanding of the nature of dark matter. It is well known that dark matter plays a critical role in shaping the gravitational potential of galaxies, yet its exact nature remains elusive. The distribution of stars, gas, and dark matter in kiloparsec rings might offer indirect clues about the properties of dark matter and how it influences the formation of galactic structures. For instance, the way gas is funneled into a ring by gravitational forces may differ if the amount of dark matter in the galaxy varies, potentially giving us insights into its composition. Another exciting avenue for further exploration lies in the potential connection between kiloparsec rings and cosmic expansion. As we study the large-scale distribution of galaxies and their structures, we know that the universe itself is expanding. Could the presence of kiloparsec rings in galaxies offer a unique perspective on the rate of expansion? While this connection is still speculative, the study of galactic structures in the context of cosmic expansion could provide a deeper understanding of how the universe is evolving on the largest scales. In addition to their cosmic implications, kiloparsec rings may also hold the key to unlocking some of the most fundamental mysteries of star formation. The intense environments within these rings, where gas accumulates and condenses into stars, provide a natural laboratory for studying the processes that govern stellar birth. By examining the types of stars formed within kiloparsec rings, astronomers can investigate questions about the initial mass function, IMF, the distribution of stellar masses in a population, and how it varies in different environments. Understanding the IMF in rings could reveal how factors like gas density, metallicity, and feedback from star formation shape the types of stars that emerge. One of the most intriguing possibilities lies in the connection between kiloparsec rings and the broader process of galaxy-wide star formation. In many galaxies, kiloparsec rings are among the most active regions of star formation, contributing significantly to the galaxy's overall stellar population. However, the precise role of these rings in the broader context of galaxy evolution remains uncertain. Do they represent a transient phase in the life of a galaxy, or are they a stable feature that plays a key role in the long-term growth of the galaxy? Exploring this question could provide new insights into how galaxies grow, evolve, and interact with their environment over cosmic timescales. Additionally, the relationship between kiloparsec rings and galactic morphology deserves further scrutiny. While many galaxies with kiloparsec rings share similar characteristics, such as spiral structures or active galactic nuclei, others exhibit unique features that challenge our current understanding of galactic formation. These galaxies may possess unusually large or complex rings, suggesting that kiloparsec rings could be part of a broader class of galactic structures that have yet to be fully classified. By studying the diversity of galaxies with kiloparsec rings, astronomers can refine their models of how galaxies form and evolve, leading to a more comprehensive understanding of the variety of galactic shapes and behaviors. The study of kiloparsec rings is not limited to distant galaxies either. In our own Milky Way galaxy, astronomers are beginning to identify evidence of similar structures in our neighboring regions. While the Milky Way does not currently host a well-defined kiloparsec ring, there are hints of ring-like structures in some of its neighboring dwarf galaxies. This raises the tantalizing possibility that rings may play a more significant role in the evolution of galaxies in our cosmic neighborhood than previously thought. Investigating these nearby galaxies could provide valuable insights into the conditions under which kiloparsec rings form and evolve, offering a more direct link between distant and local galactic phenomena. Another key aspect of this research is the influence of external factors, such as interactions with other galaxies and cosmic environmental conditions. For example, when galaxies collide or pass close to each other, The gravitational forces exerted during these interactions can distort the galaxies and funnel gas into rings. These galactic collisions provide unique conditions for studying how galactic structures, including rings, evolve in response to external forces. Understanding how kiloparsec rings are affected by these interactions could shed light on the broader processes that shape galaxies in the universe. In the future, the use of gravitational lensing may offer another breakthrough in the study of kiloparsec rings. Gravitational lensing occurs when a massive object, such as a galaxy or cluster of galaxies, bends and magnifies the light from a more distant object. By studying how light from background galaxies is distorted by the gravitational influence of galaxies with kiloparsec rings, astronomers can obtain detailed information about the mass distribution, dark matter content, and internal dynamics of the rings. This technique is still in its early stages but holds tremendous potential for providing a wealth of information about the structure and behavior of these enigmatic cosmic features. Through all these exciting developments, one thing remains clear: kiloparsec rings are not just isolated phenomena, but vital pieces of the cosmic puzzle. Each new discovery, whether in the form of theoretical models, observational data, or advanced techniques, brings us one step closer to understanding the true nature of these cosmic structures. They continue to challenge our ideas about galaxies, star formation, dark matter, and the fundamental forces that shape the universe. As astronomers around the world continue to push the boundaries of our knowledge, one can only wonder what new revelations lie ahead. The study of kiloparsec rings is far from over, and with each new observation, each new theory, we are uncovering deeper layers of the cosmos. These mysterious structures, spanning vast distances across the universe, offer a glimpse into the processes that have shaped galaxies for billions of years and will continue to influence their evolution in the future. As we look toward the future of astronomy, it is clear that the mysteries of kiloparsec rings will continue to inspire wonder, discovery, and a deeper understanding of the universe in which we live. The mysteries surrounding kiloparsec rings extend into some of the most profound questions we have about the universe. One of these questions concerns the life cycle of galaxies. Galaxies are not static. They evolve over billions of years through processes like star formation, mergers, and interactions with the intergalactic medium. Kiloparsec rings, as regions of intense star formation, might represent a critical stage in this life cycle, one that is not yet fully understood. For instance, could kiloparsec rings signify a rejuvenation phase for galaxies that might otherwise see their star formation rates decline? As galaxies age, their gas reservoirs often deplete due to star formation and feedback from active galactic nuclei. However, the accumulation of gas into kiloparsec rings provides a concentrated environment where star formation can temporarily reignite, potentially giving the galaxy a new lease on life. If this is true, kiloparsec rings might play a role in extending the active, star-forming phase of galaxies, delaying their transition into quiescence. This idea ties into another significant mystery: the role of feedback mechanisms in shaping galactic evolution. Feedback from stars, supernovae, and active galactic nuclei can have a profound impact on the surrounding interstellar medium. It can compress gas, triggering new waves of star formation, or expel gas, shutting down star formation entirely. Within kiloparsec rings, these feedback processes are particularly intense due to the high density of stars and supernovae. Understanding how feedback operates in these environments could provide valuable insights into the broader role it plays in the evolution of galaxies. Moreover, kiloparsec rings offer a unique perspective on the interplay between galaxies and their environments. Galaxies do not exist in isolation. They are embedded in the cosmic web, a vast network of filaments and voids composed of dark matter, gas, and galaxies. The interactions between galaxies and their environments can influence the formation of kiloparsec rings. For example, gas from the cosmic web might be funneled into a galaxy, providing the raw material for a ring. Alternatively, interactions with other galaxies, such as tidal forces or mergers, could disrupt a galaxy's structure and lead to the formation of a ring. These interactions also raise questions about the longevity of kiloparsec rings. Are these rings stable, long-lived structures, or are they transient features that eventually dissipate? Observations of kiloparsec rings in different galaxies suggest that both scenarios might be possible, depending on the specific conditions. Rings that form in isolated galaxies might be more stable, while those formed through interactions might be more short-lived, as the forces that create them also contribute to their eventual dispersal. Understanding the factors that determine the lifespan of kiloparsec rings is a critical area of research, one that has implications for our broader understanding of galactic dynamics. Another fascinating aspect of kiloparsec rings is their potential to act as cosmic time capsules. The stars within these rings provide a record of the conditions under which they formed, much like fossils and sedimentary rock layers provide a record of Earth's past environments. By studying the ages, compositions, and motions of stars in kiloparsec rings, astronomers can piece together the history of star formation in these regions. This, in turn, can reveal how the conditions within a galaxy have changed over time, offering a glimpse into its evolutionary history. Kiloparsec rings also provide a natural laboratory for testing theories of star formation. While the basic process of star formation is relatively well understood, many details remain elusive, particularly when it comes to the influence of environment. The high-density, high-pressure conditions within kiloparsec rings are unlike those in most other parts of galaxies. These extreme conditions might lead to differences in the types of stars that form, their distribution, and their initial mass function. By comparing the properties of stars in kiloparsec rings to those in other regions, astronomers can refine their models of star formation and test their predictions against real-world data. One of the most exciting frontiers in the study of kiloparsec rings is the potential to use them as probes of the cosmic environment. Because these rings are so sensitive to their surroundings, they can act as indicators of the larger-scale processes occurring in the universe. For example, changes in the properties of kiloparsec rings might reflect changes in the inflow of gas from the cosmic web or the influence of large-scale structures like galaxy clusters. By studying these connections, astronomers can gain a better understanding of how galaxies fit into the broader context of the universe. As we look to the future, the study of kiloparsec rings stands to benefit greatly from advances in observational technology. Next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are already providing unprecedented views of galaxies and their structures. These instruments are capable of resolving the fine details of kiloparsec rings, including their internal dynamics and the properties of their constituent stars. With these tools, astronomers can probe deeper into the mysteries of kiloparsec rings, uncovering new details about their formation, evolution, and role in the cosmos. In addition to observational advances, improvements in computational modeling are providing new insights into kiloparsec rings. Simulations of galaxy evolution, which incorporate the complex interplay of gravity, gas dynamics, star formation, and feedback, are becoming increasingly sophisticated. These models can replicate the conditions under which kiloparsec rings form and evolve, allowing astronomers to test hypotheses and explore scenarios that are difficult to observe directly. By comparing the results of simulations to observations, researchers can refine their models and develop a more complete understanding of these enigmatic structures. Kiloparsec rings are also inspiring new theoretical work on the fundamental physics of galaxies. For example, the distribution of matter within kiloparsec rings raises questions about the role of dark matter in shaping galactic structures. Observations suggest that the gravitational potential of dark matter halos plays a critical role in guiding the flow of gas and the formation of rings. However, the details of this interaction are still poorly understood. By studying kiloparsec rings, astronomers can test predictions about the distribution and properties of dark matter, potentially shedding light on one of the most profound mysteries of modern astrophysics. As we uncover more about kiloparsec rings, it becomes increasingly clear that they are not just isolated phenomena but integral components of the cosmic story. They connect the small-scale processes of star formation to the large-scale structure of the universe, offering a unique perspective on the interplay between matter, energy, and gravity. Each discovery brings us closer to answering fundamental questions about the nature of the universe, while also raising new questions that challenge our understanding. The narrative of kiloparsec rings, much like the universe they inhabit, is ever-expanding, branching into areas of inquiry that were previously unimaginable. One of the most compelling threads lies in the potential connection between kiloparsec rings and galactic feedback mechanisms, particularly those involving supermassive black holes at the centers of galaxies. These black holes, often millions or billions of times the mass of the Sun, are known to influence their host galaxies through jets of high-energy particles and intense radiation, collectively referred to as active galactic nuclei, AGN. But how exactly do these AGN interact with kiloparsec rings? Observational data suggests that the influence of an AGN can vary widely. In some cases, the energy released by the AGN can compress surrounding gas, triggering waves of star formation within the ring. In others, this energy might expel gas from the central regions of the galaxy, starving the ring of the material needed to sustain star formation. This duality, where AGN activity can either fuel or inhibit the formation of stars, is a fascinating area of study that underscores the complexity of galaxy evolution. Further complicating the picture is the role of molecular clouds within kiloparsec rings. These dense regions of gas and dust are the birthplaces of stars, and their behavior is a critical factor in the dynamics of the rings. Observations reveal that molecular clouds within kiloparsec rings are subject to intense gravitational forces, turbulence, and interactions with shock waves from supernovae. These conditions can lead to rapid bursts of star formation, but they can also tear clouds apart, halting the process. Understanding the balance between these competing forces is key to unraveling the secrets of kiloparsec rings. Another intriguing question concerns the metallicity of kiloparsec rings. Metallicity refers to the abundance of elements heavier than hydrogen and helium, which are produced in the cores of stars and dispersed into the interstellar medium through processes like supernova explosions. Kiloparsec rings, with their high rates of star formation, are hotspots for such enrichment. Studying the metallicity of these regions can provide clues about their age, the efficiency of star formation, and the history of gas inflow and outflow in the galaxy. The metallicity of kiloparsec rings also has implications for the formation of planets. The presence of heavy elements is a critical factor in the formation of rocky planets like Earth. If kiloparsec rings are enriched with metals, they might represent regions where planet formation is particularly likely, at least under the right conditions. This raises fascinating possibilities for the existence of planetary systems, and potentially even life, in these extraordinary environments. On a larger scale, kiloparsec rings might also offer insights into the structure and behavior of galaxy clusters. Galaxy clusters are among the largest structures in the universe, containing hundreds or thousands of galaxies bound together by gravity. The interactions between galaxies within a cluster can have dramatic effects, including the formation of kiloparsec rings. For instance, when galaxies pass close to one another, the resulting tidal forces can funnel gas into the central regions of the galaxies, triggering ring formation. By studying these interactions, astronomers can learn more about the dynamics of galaxy clusters and the role they play in shaping the universe. Kiloparsec rings are not only a window into the processes of star formation and galactic evolution, but also a reminder of the intricate and interconnected nature of the cosmos. They challenge us to think about galaxies not as isolated systems but as parts of a larger, dynamic network. They invite us to explore the relationships between the smallest particles and the largest structures, between the forces of creation and destruction, and between the known and the unknown. This interconnectedness is perhaps best illustrated by the potential role of kiloparsec rings in the distribution of baryonic matter, the normal matter that makes up stars, planets, and living beings. While baryonic matter accounts for only a small fraction of the universe's total mass energy content, its distribution is a critical piece of the cosmic puzzle. Kiloparsec rings, as regions of concentrated star formation, might serve as markers of where baryonic matter is accumulating. By mapping these rings across the universe, astronomers could gain new insights into the distribution of matter and the underlying structure of the cosmos. Moreover, the study of kiloparsec rings is pushing the boundaries of our technological capabilities. Advanced telescopes equipped with adaptive optics, such as the Very Large Telescope, VLT, and space-based observatories like the Hubble Space Telescope and James Webb Space Telescope are providing unprecedented views of these structures. These instruments allow astronomers to observe kiloparsec rings in incredible detail, from the individual stars within them to the large-scale flows of gas that sustain them. The data collected by these telescopes are not only deepening our understanding of kiloparsec rings but also driving innovations in imaging, spectroscopy, and computational analysis. Simultaneously, the study of kiloparsec rings is fostering international collaboration on a scale that mirrors the vastness of the universe itself. Projects like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Square Kilometer Array, SKA, involve teams of scientists from around the globe, working together to unravel the mysteries of the cosmos. These collaborations are not only advancing our knowledge of kiloparsec rings but also demonstrating the power of collective human effort in the pursuit of discovery. As we continue to explore kiloparsec rings, we are reminded of the broader significance of this research. These structures are not just astronomical curiosities. They are key pieces of the puzzle in our quest to understand the universe. They challenge our assumptions, inspire new questions, and drive us to push the boundaries of what we know. They remind us that the cosmos is not static but dynamic, filled with processes that are as beautiful as they are complex. And perhaps most importantly, the study of kiloparsec rings invites us to reflect on our place in the universe. These structures, born of the interplay between matter, energy, and gravity, are a testament to the creativity of the cosmos. They are a reminder that even in the vastness of space, patterns emerge, and order arises from chaos. They are a celebration of the universe's ability to create, destroy, and transform, a cycle that mirrors the rhythms of life itself. As we look up at the night sky and ponder the mysteries it holds, let us remember the kiloparsec rings, cosmic jewels that light the way to understanding not just the universe, but also our own existence within it. Kiloparsec rings also highlight an important philosophical question, the concept of scale. When we examine these massive structures, spanning thousands of light years, it's easy to feel insignificant. Yet, our ability to study them, to ask questions about their origins and implications, is a profound testament to the capabilities of human curiosity and intellect. These rings might dwarf entire galaxies, but they also serve as a reminder of how far we've come in understanding the universe and our place within it. On the microscopic level, kiloparsec rings remind us of the fundamental building blocks of the cosmos. Hydrogen atoms, the simplest and most abundant element in the universe, are the primary fuel for star formation. Within kiloparsec rings, hydrogen gas is compressed and heated, undergoing nuclear fusion to form helium and, eventually, heavier elements. This process, occurring on scales incomprehensibly larger than human experience, is the foundation for the creation of everything: planets, life, and the very atoms that make up our bodies. The life cycle of kiloparsec rings is another fascinating aspect to consider. These structures are not permanent. They are transient features in the cosmic timeline. Over millions of years, they evolve, change, and eventually dissipate. The intense star formation within them consumes the available gas, and without a constant influx of new material, the ring's activity slows and fades. However, the stars that form within these rings continue to shine, spreading the elements forged in their cores throughout the galaxy. This means that kiloparsec rings, even as they vanish, leave an indelible mark on the universe. Furthermore, the distribution of kiloparsec rings across the cosmos poses an intriguing question about their prevalence and variability. Are these structures common in galaxies, or are they rare phenomena? Current observations suggest that certain types of galaxies, particularly barred spiral galaxies, are more likely to host kiloparsec rings. The presence of a bar, a linear structure of stars and gas extending from the galaxy's center, can create gravitational forces that funnel material into the central regions, forming a ring. However, the exact conditions needed to produce a kiloparsec ring remain a subject of ongoing research. Another layer of complexity is added when we consider the influence of dark matter on kiloparsec rings. Dark matter, an invisible substance that makes up most of the universe's mass, exerts gravitational forces that shape the structure and behavior of galaxies. While dark matter cannot be observed directly, its effects can be inferred from the motions of stars and gas within galaxies. In the context of kiloparsec rings, dark matter halos might play a role in stabilizing these structures or influencing the flow of gas that fuels star formation. The connection between kiloparsec rings and dark energy is also worth exploring. Dark energy, the mysterious force driving the accelerated expansion of the universe, impacts the large-scale structure of the cosmos. While its effects are most noticeable on intergalactic scales, dark energy could indirectly influence processes within galaxies, including the formation and evolution of kiloparsec rings. Understanding these connections requires a synthesis of observations, simulations, and theoretical models, a task that challenges even the most advanced tools in modern astronomy. On an observational level, one of the most exciting frontiers is the search for kiloparsec rings in the early universe. Using telescopes like the James Webb Space Telescope, JWST, astronomers are peering back in time to study galaxies as they appeared billions of years ago. Discovering kiloparsec rings in these ancient galaxies would provide valuable insights into their formation and evolution over cosmic time. It could also reveal how the conditions in the early universe differed from those today, shedding light on the processes that shape the cosmos as we know it. Technological advancements in astronomy are playing a crucial role in this research. Instruments capable of capturing high-resolution images and detailed spectra are allowing scientists to study kiloparsec rings with unprecedented clarity. These tools are not only revealing the intricate structures within the rings but also enabling the measurement of physical properties like temperature, density, and chemical composition. Combined with sophisticated computer simulations, these observations are helping to create a more complete picture of kiloparsec rings and their role in the universe. The cultural and historical context of our study of kiloparsec rings is another layer worth considering. Throughout history, humanity has looked to the stars for inspiration, guidance, and meaning. Kiloparsec rings, with their awe-inspiring scale and beauty, continue this tradition. They are a modern symbol of the mysteries that lie beyond our world, a reminder that there is always more to discover. They also challenge us to think about the future of exploration. What new tools and technologies will we develop to study these rings, and what new questions will arise as a result? Kiloparsec rings invite us to ponder the philosophical implications of our place in the universe. These structures, formed by the interplay of natural forces over billions of years, are a testament to the power of the cosmos to create order and complexity. At the same time, they remind us of the vastness of space and time, and the relatively small role we play within it. Yet, our ability to understand and appreciate these phenomena is a testament to the power of human curiosity and ingenuity. Kiloparsec rings are more than just a subject of scientific inquiry. They are a source of wonder, inspiration, and a reminder of the interconnectedness of all things. They challenge us to look beyond the limits of our understanding, to embrace the unknown, and to continue exploring the mysteries of the universe. As we delve even deeper into the intricacies of kiloparsec rings, their role as a bridge between the microscopic and macroscopic components of the universe becomes even more fascinating. They are a nexus where individual atoms of hydrogen coalesce to create massive, luminous stars, and yet, they also interact with the colossal gravitational forces exerted by the galaxy as a whole. This interplay highlights one of the central themes in astronomy: how the smallest building blocks of matter contribute to the grand architecture of the cosmos. Kiloparsec rings provide us with an opportunity to study galaxy dynamics in action. These rings are not static, they are dynamic, constantly changing due to gravitational interactions, feedback from star formation, and the inflow and outflow of gas. They serve as laboratories where we can observe how galaxies evolve over time. By studying kiloparsec rings, astronomers can test theories of galactic evolution, such as the impact of mergers, the role of supermassive black holes, and the feedback processes that regulate star formation. The feedback mechanisms in kiloparsec rings are particularly intriguing. When massive stars form, they emit intense radiation and strong stellar winds. These processes can heat the surrounding gas, making it less likely to collapse into new stars. In some cases, the energy released by supernovae, explosions that mark the end of a massive star's life, can blow gas out of the ring entirely, halting star formation. However, this feedback can also trigger new waves of star formation by compressing the surrounding gas. This delicate balance between suppression and stimulation of star formation is a key factor in understanding the life cycle of kiloparsec rings. Adding to the complexity is the role of magnetic fields. While often overlooked in discussions about galaxy evolution, magnetic fields are an essential component of the interstellar medium. They can influence the motion of gas within kiloparsec rings, affecting how and where stars form. Observations using radio telescopes have started to reveal the magnetic structures within these rings, providing new insights into their role in star formation and galactic dynamics. The interplay between kiloparsec rings and their host galaxies also raises questions about their long-term stability. What factors determine whether a kiloparsec ring will persist for hundreds of millions of years or dissipate after a shorter lifespan? Some rings appear to be fueled by a steady supply of gas, possibly channeled by the galaxy's bar or spiral arms. Others may form during specific events, such as galaxy mergers, and gradually fade as the conditions that created them change. Understanding these factors is critical for constructing a complete picture of galactic evolution. Another layer of intrigue lies in the chemical enrichment of kiloparsec rings. The stars that form within these rings create heavier elements through nuclear fusion, and when they die, they release these elements into the surrounding gas. Over time, this process enriches the gas within the ring, leading to a higher abundance of elements like carbon, oxygen, and iron. This chemical enrichment is not only important for understanding the life cycle of kiloparsec rings but also has broader implications for the formation of planets and, potentially, life. The diversity of kiloparsec rings across galaxies is another area ripe for exploration. Some rings are nearly perfect circles, while others are more elliptical or irregular. This variation reflects differences in the physical conditions of their host galaxies, such as the distribution of gas, the presence of a bar, and the influence of nearby galaxies. By comparing kiloparsec rings in different environments, astronomers can gain a better understanding of the factors that influence their formation and evolution. Advances in computational modeling are also shedding light on the mysteries of kiloparsec rings. Simulations allow scientists to recreate the conditions under which these rings form and evolve, providing a way to test hypotheses and explore scenarios that would be impossible to observe directly. These models are becoming increasingly sophisticated, incorporating factors like magnetic fields, feedback processes, and the influence of dark matter. By comparing the results of these simulations with real observations, astronomers can refine their understanding of kiloparsec rings and their role in the universe. One of the most exciting developments in this field is the discovery of kiloparsec rings in galaxies beyond our local group. With powerful telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope, astronomers are identifying kiloparsec rings in distant galaxies, providing a window into their prevalence and properties across cosmic time. These observations are helping to answer questions about how common these structures are, and whether their characteristics change in different galactic environments. The implications of kiloparsec rings extend beyond astronomy, touching on broader scientific and philosophical questions. For example, the processes occurring within these rings are a microcosm of the universe's ability to create complexity from simplicity. Hydrogen atoms, formed shortly after the Big Bang, are transformed through nuclear fusion into the elements that make up stars, planets, and even living organisms. This progression from the simplest building blocks to the intricate structures we observe today is a recurring theme in the study of the cosmos. Kiloparsec rings also challenge us to think about the interconnectedness of the universe. The stars that form within these rings are not isolated entities. They are part of a larger galactic ecosystem. Their formation is influenced by the gravitational forces, gas dynamics, and magnetic fields of the galaxy, and in turn, they shape their environment through feedback processes. This interconnectedness highlights the complexity of the universe and the need for a holistic approach to understanding it. In the context of human exploration and discovery, kiloparsec rings are a reminder of how far we have come and how much we have yet to learn. They are a testament to the power of modern astronomy, which has transformed our view of the universe from a static and unchanging cosmos to a dynamic and ever-evolving tapestry of stars, galaxies, and cosmic phenomena. They also serve as a source of inspiration, encouraging us to continue exploring the unknown and pushing the boundaries of what is possible. As we continue to study kiloparsec rings, new questions are sure to arise. What role do these structures play in the larger cosmic web that connects galaxies across the universe? How do they interact with other galactic features, such as spiral arms, bars, and bulges? What can they tell us about the conditions in the early universe and the processes that led to the formation of the first galaxies? The answers to these questions will require a combination of observational ingenuity, theoretical insight, and technological innovation. They will also require a willingness to embrace the unknown and to explore the universe with an open mind. Kiloparsec rings are not just objects of scientific study. They are symbols of the human spirit of curiosity and discovery, reminding us of our place in the cosmos and our capacity to understand it. The study of kiloparsec rings continues to be one of the most captivating areas in astronomy, not just for the breathtaking visuals they provide but for the profound scientific mysteries they represent. As telescopes and detection techniques become more advanced, we are beginning to uncover a wealth of information about these massive cosmic structures. Each new discovery reshapes our understanding of their role in the grander cosmic design. One of the most compelling questions about kiloparsec rings is how they evolve over time. These structures are not static snapshots of galactic activity but dynamic regions undergoing constant transformation. The processes of star formation, feedback from massive stars, and interactions with surrounding galactic material all contribute to this evolution. By studying kiloparsec rings in galaxies of different ages and stages of development, astronomers can piece together a timeline of their formation and eventual dissolution. A fascinating aspect of this evolution is the phenomenon of starburst activity within kiloparsec rings. Starbursts are periods of extremely rapid star formation, during which a significant portion of a galaxy's gas is converted into stars over a relatively short time. These events often occur in kiloparsec rings, where the concentration of gas and the physical conditions are ideal for triggering such intense activity. Observing starbursts in kiloparsec rings provides insights into the mechanisms that drive these bursts and their impact on the surrounding galaxy. Starbursts in kiloparsec rings also have significant implications for the broader galactic ecosystem. The intense radiation and stellar winds produced by massive stars can heat and expel gas from the ring, creating large cavities in the interstellar medium. In some cases, this expelled gas can escape the galaxy entirely, contributing to the enrichment of the intergalactic medium. This process, known as galactic feedback, is a critical factor in regulating star formation and shaping the evolution of galaxies. However, feedback processes are not entirely destructive. In many cases, they can compress gas in nearby regions, triggering new waves of star formation. This phenomenon, known as triggered star formation, creates a ripple effect that propagates through the kiloparsec ring. Observing and modeling these feedback processes helps astronomers understand the delicate balance between the forces that drive and inhibit star formation, a balance that plays a crucial role in the life cycle of galaxies. Another area of active research involves the relationship between kiloparsec rings and supermassive black holes. Nearly every galaxy with a kiloparsec ring hosts a supermassive black hole at its center, and the interaction between the two is a topic of intense study. While the black hole exerts a gravitational influence on the surrounding gas, the star formation activity in the ring can, in turn, influence the accretion of material onto the black hole. This interplay may help explain the observed correlation between the mass of a galaxy's central black hole and the properties of its bulge. Interestingly, kiloparsec rings may also play a role in the fueling of active galactic nuclei, AGN. AGNs are regions of intense radiation powered by material accreting onto a supermassive black hole. In some cases, the inflow of gas from the kiloparsec ring to the central regions of the galaxy may provide the fuel needed to sustain AGN activity. Observing kiloparsec rings in galaxies with active AGNs can help astronomers understand the mechanisms that drive these powerful phenomena. The distribution of molecular gas within kiloparsec rings is another intriguing area of study. Molecular gas is the raw material for star formation, and its abundance and distribution within a kiloparsec ring provide clues about the processes that regulate star formation. Observations with telescopes like ALMA have revealed intricate structures within kiloparsec rings, including clumps, filaments, and spiral patterns. These structures suggest that the gas within the ring is not evenly distributed but is shaped by a combination of gravitational forces, turbulence, and feedback processes. The role of dark matter in shaping kiloparsec rings is yet another frontier of research. Dark matter, which makes up the majority of the universe's mass, exerts a gravitational influence on the visible matter within galaxies. This influence can affect the dynamics of kiloparsec rings, including their shape, rotation, and stability. By studying the motion of gas and stars within kiloparsec rings, astronomers can infer the distribution of dark matter in their host galaxies, providing valuable insights into this mysterious component of the universe. The discovery of kiloparsec rings in distant galaxies has also opened up new opportunities to study these structures in different cosmic environments. In the early universe, galaxies were more gas-rich and experienced more frequent mergers, conditions that may have been conducive to the formation of kiloparsec rings. By observing these rings at different redshifts, astronomers can trace their evolution over cosmic time and explore how their properties have changed in response to the changing conditions of the universe. In addition to their scientific significance, kiloparsec rings have a profound aesthetic and philosophical appeal. Their nearly symmetrical shapes and luminous star-forming regions make them some of the most visually striking features in the cosmos. They are a reminder of the beauty and order that can emerge from the chaotic processes of galactic evolution. For many, the sight of a kiloparsec ring is a source of inspiration, a symbol of the universe's ability to create structure and complexity on a grand scale. As we continue to explore kiloparsec rings, new technologies and methods are expanding the boundaries of what we can observe and understand. Advances in high-resolution imaging, spectroscopy, and computational modeling are providing unprecedented insights into these fascinating structures. Each new discovery brings us closer to unraveling the mysteries of kiloparsec rings and their role in the cosmic tapestry. The study of kiloparsec rings is a testament to the power of human curiosity and ingenuity. These structures, once hidden in the depths of space, have become a window into the processes that shape the universe. They remind us of the interconnectedness of all things, from the smallest particles of gas to the grandest galaxies, and they challenge us to continue exploring the unknown with an open mind and a sense of wonder. Kiloparsec rings also reveal the fascinating interplay between physics, chemistry, and environmental influences in shaping the cosmos. These structures, formed in the dynamic environments of galaxies, operate under an intricate set of physical laws. Within them, gravitational forces, magnetic fields, radiation pressure, and the flow of interstellar gas all work together to create a stage for one of the most profound phenomena in the universe, the birth of stars. One of the remarkable aspects of these rings is how finely tuned the conditions need to be for them to form and persist. Gravity acts as the main architect, drawing gas and dust into orbiting rings. However, it's not just gravity at play. Feedback mechanisms like supernovae explosions and stellar winds continuously inject energy into the system. These forces sometimes disrupt the ring's structure, yet paradoxically, they also compress certain regions, triggering bursts of star formation. This feedback loop between creation and destruction is a central theme in understanding kiloparsec rings. Moreover, the molecular composition of the gas in these rings holds keys to understanding their dynamics. Hydrogen, the most abundant element in the universe, exists in its molecular form, H2, within kiloparsec rings, creating dense clouds that become stellar nurseries. Other elements and molecules, such as carbon monoxide (CO), serve as tracers that astronomers use to map these regions. Observations of these tracers with instruments like ALMA, Atacama Large Millimeter/Submillimeter Array, have revealed incredible details about the temperature, density, and motion of the gas. Interestingly, not all kiloparsec rings are the same. They vary significantly in size, brightness, and activity levels. Some are dense and luminous, glowing brightly in ultraviolet and infrared wavelengths due to intense star formation. Others are more subdued, their gas reservoirs slowly depleting over time. These differences often depend on the type of galaxy they reside in. For example, barred spiral galaxies frequently host highly active kiloparsec rings, as the bars act as funnels, channeling gas inward. On the other hand, elliptical galaxies, which are more gas-poor, rarely exhibit such structures. The longevity of kiloparsec rings is another intriguing question. While individual stars within the ring have lifespans ranging from millions to billions of years, the ring itself is a transient feature on cosmic timescales. Interactions with other galaxies, internal instabilities, or a depletion of available gas can lead to the dissolution of the ring. Observing galaxies at various stages of their life cycle allows astronomers to piece together the story of how these structures emerge and fade away. Another important dimension of kiloparsec rings lies in their connection to galactic scale phenomena, particularly their role in regulating star formation across entire galaxies. These rings act as a sort of star-forming engine, concentrating resources and driving bursts of activity. This has implications for the overall evolution of their host galaxies. Galaxies with active kiloparsec rings often display vibrant, youthful star populations, while those without rings tend to age more rapidly, with their star formation activity declining over time. The presence of kiloparsec rings in merging galaxies adds yet another layer of complexity to their study. Galaxy mergers are chaotic, high-energy events that can completely transform the structure of the galaxies involved. During these mergers, tidal forces can redistribute gas and stars, sometimes leading to the formation of massive kiloparsec-scale rings. These merger-induced rings are often among the brightest and most active, as the collision compresses gas to extreme densities, triggering intense starbursts. By studying these rings, astronomers can gain a better understanding of how galaxy mergers influence star formation and structure. One particularly fascinating case of a kiloparsec ring associated with a merger is the Cartwheel galaxy. This galaxy's iconic ring-like appearance resulted from a smaller galaxy passing through its center, triggering a ripple effect of star formation that propagated outward. The Cartwheel galaxy serves as a vivid example of how kiloparsec rings can emerge in the aftermath of cosmic collisions, transforming chaos into order. In addition to their scientific importance, kiloparsec rings also have implications for our understanding of galactic aesthetics and cosmic beauty. These rings often appear as luminous halos or bands of light encircling the central regions of galaxies, creating some of the most visually stunning images captured by telescopes. They serve as a reminder of the elegance and intricacy of the universe, inspiring awe and wonder in those who observe them. Beyond their beauty and scientific intrigue, kiloparsec rings are also valuable tools for probing fundamental questions about the universe. They offer a natural laboratory for studying the interplay of forces that govern star formation, galactic dynamics, and even the behavior of dark matter. The precise rotation curves of kiloparsec rings, for example, have provided some of the most compelling evidence for the existence of dark matter. By analyzing how the ring's stars and gas move under the influence of gravity, astronomers can infer the presence of unseen mass, shedding light on one of the most elusive components of the universe. As our observational capabilities continue to improve, the study of kiloparsec rings is poised to enter a new era. Next-generation telescopes like the James Webb Space Telescope, JWST, are already revealing unprecedented details about these structures, capturing their formation processes and inner workings with unparalleled clarity. Meanwhile, advances in computational modeling allow scientists to simulate the complex interactions that give rise to kiloparsec rings, providing new insights into their origins and evolution. Despite all that we have learned, there is still so much more to discover about kiloparsec rings. Their diversity, complexity, and connection to the broader universe make them an endlessly fascinating subject of study. Each observation, each simulation, and each new discovery adds another piece to the puzzle, bringing us closer to a complete understanding of these cosmic masterpieces. And yet, as with all great mysteries of the universe, the more we learn, the more questions arise. What are the precise conditions required for kiloparsec rings to form? How do they interact with their host galaxies on long timescales? What role do they play in the broader narrative of cosmic evolution? These questions continue to drive astronomers to explore, to observe, and to push the boundaries of what we know. Kiloparsec rings stand as a testament to the incredible complexity and beauty of the universe. They remind us that even in the vastness of space, intricate patterns and structures emerge, governed by the same fundamental laws that shape our world. They challenge us to look deeper, to ask bigger questions, and to marvel at the wonders of the cosmos. The story of kiloparsec rings is not just a story of stars, gas, and galaxies, it's a story of cosmic interconnectedness. These rings are the crossroads where various forces and phenomena converge, creating an environment rich in complexity and activity. They embody the duality of chaos and order, showing us how seemingly random forces can produce structured beauty. The influence of kiloparsec rings on their host galaxies extends far beyond their physical boundaries. For example, the star formation that occurs within these rings can dramatically alter the chemical composition of a galaxy. Stars forge heavier elements in their cores through nuclear fusion, and when they die, they release these elements back into the interstellar medium. This process, often referred to as chemical enrichment, helps seed the galaxy with the building blocks for future generations of stars, planets, and potentially life itself. In galaxies with active kiloparsec rings, this cycle of enrichment is particularly intense. The rapid pace of star formation ensures a steady supply of newly minted elements, which can then be incorporated into subsequent generations of stars and planets. This process highlights the profound role that kiloparsec rings play in the broader context of galactic evolution. They are not just passive features but active participants in shaping the destiny of their galaxies. Moreover, kiloparsec rings are intricately tied to the distribution of dark matter within their host galaxies. The motion of gas and stars within these rings often reveals discrepancies that cannot be explained by visible matter alone. These discrepancies are attributed to dark matter, the mysterious substance that makes up roughly 27% of the universe's total mass energy content. By studying the dynamics of kiloparsec rings, astronomers can infer the distribution and density of dark matter, shedding light on one of the most enigmatic components of the cosmos. Another intriguing aspect of kiloparsec rings is their role in the larger cosmic web, the vast network of filaments and voids that connects galaxies across the universe. These rings are not isolated phenomena. They are influenced by and, in turn, influence their surroundings. For example, interactions with nearby galaxies or large-scale flows of gas can trigger the formation of kiloparsec rings or alter their structure. This interconnectedness underscores the idea that no part of the universe exists in isolation. Every structure, from the smallest star to the largest galaxy, is part of a larger, dynamic system. The variety of kiloparsec rings observed in the universe is also a testament to the diversity of galactic environments. Some rings are relatively small and compact, concentrated around the central regions of their host galaxies. Others are sprawling, extending across vast distances and encompassing a significant portion of the galaxy. The reasons for these differences are complex and multifaceted, involving factors such as the galaxy's mass, its history of interactions, and the distribution of gas within it. The study of kiloparsec rings also provides valuable insights into the life cycle of galaxies. These rings often serve as indicators of a galaxy's evolutionary stage. For instance, galaxies with active kiloparsec rings are typically in a phase of intense star formation, suggesting they are relatively young or have recently undergone a rejuvenating event, such as a merger or the infall of fresh gas. In contrast, older, more evolved galaxies often lack such features, having consumed or dispersed much of their available gas. As astronomers continue to study kiloparsec rings, they are uncovering new layers of complexity. One emerging area of research focuses on the role of magnetic fields in shaping these structures. Magnetic fields, though invisible, exert a significant influence on the behavior of gas and dust within galaxies. They can guide the flow of material, stabilize star-forming regions, and even affect the propagation of cosmic rays. By incorporating magnetic fields into their models, scientists are gaining a more nuanced understanding of how kiloparsec rings form and evolve. Another frontier in the study of kiloparsec rings is the exploration of their connection to supermassive black holes. Many galaxies with kiloparsec rings host active galactic nuclei, AGN, extremely luminous regions powered by material falling into a central black hole. The interplay between the AGN and the ring can be both constructive and destructive. On the one hand, the energy output from the AGN can compress gas in the ring, triggering star formation. On the other hand, intense radiation and outflows from the AGN can strip away gas, quenching star formation. Understanding this delicate balance is a key challenge for astronomers. One particularly intriguing possibility is that kiloparsec rings might serve as a kind of regulator for galactic activity. By concentrating gas in a specific region, they can moderate the flow of material into the central black hole, influencing the activity of the AGN. This feedback loop between the ring, the AGN, and the surrounding galaxy is a vivid example of the interconnectedness that characterizes the cosmos. The future of kiloparsec ring research is bright, thanks to a new generation of telescopes and instruments. Observatories like the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, promise to revolutionize our ability to observe these structures, providing unprecedented detail and sensitivity. These advancements will allow scientists to probe the smallest scales of star formation within kiloparsec rings, unraveling the microphysics that govern their behavior. Simultaneously, advances in computational power are enabling more sophisticated simulations of kiloparsec rings. These simulations can recreate the conditions under which these rings form, evolve, and interact with their surroundings, offering valuable insights that complement observational data. By combining observations with simulations, astronomers can test their theories and refine their understanding of these enigmatic structures. Kiloparsec rings are a reminder of the universe's boundless creativity and complexity. They challenge us to think big, to ask bold questions, and to explore the unknown. As we continue to study these cosmic masterpieces, we not only learn more about the universe but also about our place within it. The story of kiloparsec rings is a story of discovery, connection, and wonder, a story that invites us to look up, to imagine, and to dream. The narrative of kiloparsec rings is far from complete. These structures serve as an open-ended puzzle, continually inviting new interpretations, questions, and discoveries. Every piece of data collected reveals a layer of their intricate behavior, but each discovery also highlights the vastness of what remains unknown. This constant interplay between knowledge and mystery fuels our drive to explore these cosmic phenomena further. One area that has garnered significant interest is the potential role kiloparsec rings play in galactic mergers and interactions. When galaxies interact or collide, the gravitational forces at play can distort their shapes, redistribute their gas and stars, and ignite bursts of star formation. Kiloparsec rings often form as a direct result of such interactions, acting as the signature left behind by these cosmic encounters. They are like the aftermath of a celestial dance, frozen in time yet dynamic in their ongoing evolution. Galactic mergers are among the most violent processes in the universe, yet they often result in the creation of some of the most beautiful and structured formations, such as kiloparsec rings. During these events, gas clouds are compressed and funneled into specific regions, often forming the dense rings where star formation is most active. These rings act as a window into the galaxy's past, offering clues about the nature of its interaction and the forces at play during its transformation. Astronomers have also begun to investigate how kiloparsec rings influence the long-term evolution of galaxies. For instance, the intense star formation in these rings depletes the available gas, which can lead to the eventual cessation of star formation in the galaxy as a whole. This phenomenon, known as quenching, marks a galaxy's transition from an active, star-forming state to a more passive, quiescent one. By studying kiloparsec rings, scientists can gain insights into the processes that drive this critical phase of galactic life. The role of kiloparsec rings in regulating galactic feedback processes is another fascinating area of study. Feedback occurs when energy from stars, supernovae, or active galactic nuclei is injected back into the surrounding medium, influencing its dynamics. In kiloparsec rings, the concentrated star formation can lead to intense feedback effects, such as powerful stellar winds and supernova explosions. These processes can heat the surrounding gas, drive outflows, and even halt further star formation, illustrating the self-regulating nature of these cosmic structures. In addition to their physical and dynamic properties, kiloparsec rings are also studied for their potential as time capsules. The stars within these rings hold information about the conditions under which they formed, such as the metallicity, chemical composition, and temperature of the gas at that time. By analyzing the light from these stars, astronomers can reconstruct the history of the ring and, by extension, the host galaxy. This kind of stellar archaeology provides a powerful tool for understanding the life cycles of galaxies. Another layer of intrigue surrounding kiloparsec rings lies in their connection to supernova remnants and stellar nurseries. The intense star formation within these rings leads to a higher incidence of massive stars, which eventually end their lives in spectacular supernova explosions. These explosions not only enrich the surrounding medium with heavier elements, but also trigger the formation of new stars by compressing nearby gas clouds. This cyclic process of destruction and creation is a defining feature of kiloparsec rings, highlighting their role as engines of cosmic renewal. The study of kiloparsec rings is also expanding into the realm of multi-wavelength astronomy. Observing these rings in different parts of the electromagnetic spectrum, such as X-rays, ultraviolet, infrared, and radio, reveals different aspects of their nature. For example, ultraviolet observations highlight regions of active star formation, while infrared data provide insights into the distribution of dust and cooler gas. X-ray observations, on the other hand, can reveal the high-energy phenomena associated with supernova remnants and active galactic nuclei. This multifaceted approach allows astronomers to build a more complete picture of kiloparsec rings and their role in the cosmos. Emerging technologies and methods, such as machine learning and artificial intelligence, are also being applied to the study of kiloparsec rings. These tools can analyze vast datasets from telescopes and simulations, identifying patterns and correlations that might be missed by human researchers. For instance, machine learning algorithms can classify galaxies with kiloparsec rings based on their morphological properties, helping to identify trends and anomalies in their formation and evolution. One particularly promising avenue for future research involves the use of gravitational wave observatories. These instruments detect ripples in spacetime caused by cataclysmic events, such as the merging of black holes or neutron stars. If kiloparsec rings are associated with such events, gravitational wave data could provide a new way to study their origins and dynamics. This interdisciplinary approach underscores the interconnected nature of modern astrophysics, where different fields and techniques converge to address shared questions. As our understanding of kiloparsec rings deepens, so too does our appreciation for their broader implications. These structures remind us that the universe is not a static or isolated entity but a dynamic, interconnected system. The forces that shape kiloparsec rings are the same forces that govern the behavior of stars, galaxies, and even the large-scale structure of the cosmos. By studying these rings, we gain insights into the fundamental processes that have shaped the universe over billions of years. In many ways, kiloparsec rings are a testament to the resilience and adaptability of the cosmos. They form in response to some of the most extreme conditions imaginable, yet they emerge as sites of creation and renewal. They embody the universe's ability to transform chaos into order, to turn destruction into growth. This duality is not just a scientific curiosity, but a profound reflection of the universe's inherent beauty and complexity. The story of kiloparsec rings is far from over. With each new observation, simulation, and theory, we come closer to unraveling their mysteries. Yet, as is often the case in science, each answer raises new questions, each discovery opens new doors. This cycle of inquiry and discovery is what makes the study of kiloparsec rings, and astronomy as a whole, such a deeply rewarding endeavor. It reminds us that the universe is a vast, ever-changing tapestry, full of wonders waiting to be explored. The mysteries of kiloparsec rings continue to ripple through the collective efforts of the astronomical community, inspiring deeper investigations into their origins, properties, and significance within the broader cosmic landscape. These immense structures, teeming with star-forming activity, challenge our understanding of galactic dynamics and evolution. Each facet of their existence holds a puzzle piece to the intricate web of the universe. One of the more intriguing aspects of kiloparsec rings lies in their potential relationship with dark matter. Dark matter, an invisible and enigmatic component of the universe, exerts gravitational influence on visible matter, shaping the formation and behavior of galaxies. Scientists theorize that the distribution of dark matter could influence the stability and formation of kiloparsec rings. By mapping the movement of stars and gas within these rings, astronomers can infer the underlying dark matter distribution, potentially unlocking clues about its elusive nature. The symmetry often observed in kiloparsec rings presents another fascinating question. Why do these rings appear so well formed and circular, even in galaxies that have undergone significant disruptions? Some researchers suggest that this symmetry might result from the galaxy's attempt to reach a state of equilibrium after a turbulent event, such as a collision or interaction with another galaxy. The interplay of gravity, momentum, and angular forces creates a natural, balancing act, leading to the formation of these structured, ring-like shapes. As astronomers peer further into the cosmos with increasingly advanced telescopes, they are discovering kiloparsec rings in galaxies located billions of light-years away. These ancient structures, observed as they existed in the early universe, offer a rare glimpse into the conditions that prevailed during the epoch of galaxy formation. Studying these distant kiloparsec rings can reveal how the processes that create them may have evolved over cosmic time, providing a comparative framework for understanding their modern counterparts. The discovery of kiloparsec rings in non-spiral galaxies has also added a new dimension to their study. While they are most commonly associated with spiral galaxies, these rings have been observed in elliptical and irregular galaxies as well. This finding challenges the assumption that specific galaxy morphologies are a prerequisite for their formation. It also raises questions about the different pathways through which these rings can emerge, depending on a galaxy's shape, mass, and history. The connection between kiloparsec rings and central supermassive black holes is yet another area ripe for exploration. Many galaxies with kiloparsec rings also host active galactic nuclei, AGN, powered by supermassive black holes. The intense energy output from these AGN can influence the surrounding interstellar medium, potentially affecting the formation and evolution of kiloparsec rings. For instance, the radiation and outflows from an AGN could compress gas clouds in the ring, triggering star formation, or conversely, it could heat and disperse the gas, inhibiting further star formation. One particularly compelling hypothesis is that kiloparsec rings could act as a fuel reservoir for central black holes. The dense concentration of gas and dust in these rings provides a ready supply of material that could gradually spiral inward, feeding the black hole and sustaining its activity. This relationship creates a dynamic interplay between the central black hole and the ring, with each influencing the other's behavior over time. As we explore the physical mechanisms driving kiloparsec ring formation, we also uncover their implications for galactic ecosystems. The intense star formation in these rings enriches the surrounding environment with heavy elements, or metals, created during nuclear fusion within stars. When these stars die, they release their enriched material into the interstellar medium, contributing to the chemical evolution of the galaxy. This process not only impacts the future generation of stars but also the potential for planet formation and, by extension, the conditions necessary for life. Kiloparsec rings also serve as natural laboratories for studying the life cycles of stars. The range of stellar ages within these rings, ranging from newly formed stars to those nearing the end of their lifespans, offers a unique opportunity to observe stellar evolution in real time. By analyzing the light from these stars, astronomers can track their growth, understand their interactions with the surrounding gas, and even identify rare or exotic stellar types. Beyond their scientific significance, kiloparsec rings inspire a sense of awe and wonder. Their sheer scale, often spanning tens of thousands of light-years, defies human comprehension, while their structured beauty hints at the underlying order within the chaos of the cosmos. These rings remind us that even amidst the vast, seemingly empty expanses of space, there exist pockets of intense activity and creativity, where the universe is continually reshaping itself. Looking to the future, the next generation of telescopes and space missions promises to revolutionize our understanding of kiloparsec rings. Instruments like the James Webb Space Telescope, JWST, and the European Extremely Large Telescope, ELT, will provide unprecedented resolution and sensitivity, allowing astronomers to probe these structures in greater detail than ever before. These advancements will enable us to study the individual stars and gas clouds within kiloparsec rings, unraveling their intricate dynamics and revealing their hidden complexities. Moreover, upcoming large-scale surveys, such as those conducted by the Vera C. Rubin Observatory, will vastly expand the catalog of known kiloparsec rings, uncovering thousands of new examples across the universe. These surveys will provide the statistical data needed to identify trends and outliers, helping to refine our models and theories about these enigmatic structures. As we continue to delve into the mysteries of kiloparsec rings, we are reminded of the broader context in which they exist. These rings are not isolated phenomena but integral components of the cosmic web, a vast, interconnected network of galaxies, dark matter, and intergalactic gas. By studying kiloparsec rings, we gain insights not only into individual galaxies but also into the larger processes that have shaped the universe as a whole. The journey to understand kiloparsec rings is far from over. Each new discovery brings us closer to answering the fundamental questions they pose, yet it also opens the door to new mysteries and challenges. This ongoing cycle of exploration and discovery reflects the very essence of science, a relentless pursuit of knowledge, driven by curiosity and wonder. Kiloparsec rings, with their intricate beauty and profound implications, stand as a testament to the universe's ability to surprise, inspire, and captivate. They are a reminder of how much we have yet to learn about the cosmos, and how much there is to gain by continuing to look outward, seeking answers among the stars. As the exploration of kiloparsec rings progresses, researchers are beginning to acknowledge how these extraordinary cosmic structures may help unravel fundamental questions about the nature of galaxies. In particular, they are beginning to explore how kiloparsec rings might offer insights into the processes that drive galaxy evolution on the largest scales. At the heart of this endeavor lies the understanding of the interplay between galactic dynamics and star formation. Kiloparsec rings are regions of intense activity where gravitational forces, gas flows, and the birth of new stars converge. One of the more perplexing questions is how such rings remain stable over time despite the immense forces at play. How do they avoid collapsing inward or dissipating into the surrounding galactic environment? Scientists are delving deeper into the physics of these structures to better understand how they maintain their form for millions, even billions, of years. To answer this question, scientists are looking at the various forces that could be responsible for ring formation and stability. The first of these is the tidal forces exerted by the central bulge of the galaxy. In many cases, the nucleus of a galaxy is surrounded by a dense, massive region of stars, and the gravitational influence from this central mass may play a significant role in the creation and maintenance of kiloparsec rings. As gas flows into the central regions of the galaxy, it may be funneled into a ring-like structure due to the gravitational forces exerted by the galaxy's core. This could help explain why some rings seem to form in galaxies with particularly massive central regions. In addition to tidal forces, the motion of gas and stars within a galaxy itself is an important factor in the formation and sustainability of kiloparsec rings. The orbit of stars and gas clouds within a galaxy is not always perfectly circular or elliptical. Often, these particles follow more complex, spiraling trajectories. The interactions between stars and gas in these orbits can lead to the formation of distinct regions of gas compression, which can eventually trigger the process of star formation. This process, known as gravitational instabilities, occurs when dense pockets of gas form within the ring, creating conditions conducive to the birth of new stars. Another interesting phenomenon that may contribute to the formation of kiloparsec rings is the existence of large-scale gas flows within galaxies. These flows are the result of the galaxy's overall rotation and can be thought of as large, spiral-like currents of gas that move inward toward the galactic center. As these flows move inward, they may encounter the gravitational influence of the galactic core or other structures within the galaxy, leading to the concentration of gas into rings. These flows are often observed in galaxies with a pronounced spiral structure, where the rotation of the galaxy is particularly strong. These gas flows could also provide the necessary material for the intense star formation that characterizes kiloparsec rings. In addition to their role in star formation, kiloparsec rings can also provide important clues about the broader cosmic processes that govern galaxy evolution. The study of these rings can help scientists understand how galaxies evolve over time, how star formation occurs within different galactic environments, and how the interaction between different galactic components, such as dark matter, gas, stars, and black holes, shapes the development of a galaxy. Kiloparsec rings may also provide insights into the larger-scale processes that drive galaxy mergers and interactions. Many galaxies with prominent kiloparsec rings have undergone some form of interaction or merger in the past. These interactions can lead to the redistribution of gas and stars within the galaxy, which may trigger the formation of a ring. By studying the properties of kiloparsec rings in galaxies that have undergone interactions, astronomers hope to learn more about how these mergers influence the dynamics of star formation and the distribution of matter within a galaxy. The study of kiloparsec rings is also prompting astronomers to rethink the nature of galactic morphology itself. Traditionally, galaxies have been categorized based on their overall shape: spiral, elliptical, irregular, and so on. However, the discovery of kiloparsec rings in galaxies of varying shapes challenges this framework. For example, some irregular galaxies and elliptical galaxies have been found to contain kiloparsec rings, despite their seemingly chaotic structure. This suggests that kiloparsec rings may be a more common feature of galaxies than previously thought, and that their formation is not limited to a particular type of galaxy. This realization is pushing astronomers to expand their models of galaxy formation and to reconsider how different types of galaxies evolve over time. In the coming years, the study of kiloparsec rings will continue to benefit from advancements in observational technology. New telescopes and instruments, such as the James Webb Space Telescope, JWST, and upcoming ground-based observatories like the European Extremely Large Telescope, ELT, will allow scientists to probe these cosmic rings in unprecedented detail. With their powerful infrared capabilities, these instruments will enable astronomers to observe the complex processes occurring within kiloparsec rings, from the formation of new stars to the interaction between gas clouds and supermassive black holes. In particular, the JWST's ability to observe distant galaxies in the infrared will be invaluable in studying kiloparsec rings in the early universe. By observing these structures at different points in cosmic history, scientists can gain a better understanding of how kiloparsec rings formed in the first place and how they have evolved over time. This will help provide a clearer picture of the conditions that existed in the early universe and shed light on the processes that shaped the galaxies we observe today. Moreover, the rise of large-scale sky surveys and citizen science projects will likely contribute to the discovery of even more kiloparsec rings. By analyzing vast amounts of data from surveys like the Sloan Digital Sky Survey (SDSS) and the upcoming Vera C. Rubin Observatory, astronomers will be able to identify new examples of kiloparsec rings across the universe. This will further our understanding of how these structures are distributed throughout the cosmos and offer valuable insights into the underlying mechanisms that govern their formation. Kiloparsec rings are one of the most fascinating and enigmatic features in the universe. These colossal structures, where star formation takes place at a breathtaking scale, offer a window into the intricate processes that govern galaxy dynamics, star formation, and the interplay between different cosmic forces. As we continue to explore the mysteries of kiloparsec rings, we inch closer to answering fundamental questions about the formation and evolution of galaxies. Whether they are the result of gravitational instabilities, gas flows, or cosmic interactions, kiloparsec rings serve as a powerful reminder of the complexity and beauty of the universe. With each new discovery, we unlock more of the universe's secrets, expanding our understanding of the cosmos and our place within it. The further exploration of kiloparsec rings could significantly advance our understanding of the interplay between galactic dynamics and star formation. As more data is gathered through improved observational technology, the connection between these rings and the evolution of galaxies will become clearer. In particular, the study of kiloparsec rings may allow scientists to directly observe the mechanisms that drive star formation on galactic scales, including how gas is funneled, compressed, and triggered into the creation of new stars. This might even reveal the processes that lead to the formation of galaxy-wide structures such as spiral arms or elliptical shapes. Researchers also hypothesize that kiloparsec rings could provide insights into how the supermassive black holes at the centers of galaxies affect their surrounding environments. It's long been theorized that these black holes play a critical role in the formation of various galactic features, including the regulation of star formation. In galaxies with kiloparsec rings, the interactions between the central black hole and the surrounding gas may influence the ring's structure and star formation activity. Some studies suggest that supermassive black holes could suppress or even trigger star formation, depending on their size, age, and the surrounding galactic conditions. The relationship between the central black hole and the gas-rich regions of kiloparsec rings remains one of the most exciting areas of research in galactic dynamics. Understanding the nature of kiloparsec rings could also have profound implications for our broader understanding of the life cycle of galaxies. For instance, kiloparsec rings may provide valuable clues about the ultimate fate of a galaxy. How do they evolve over time? Do they grow, shrink, or eventually dissipate into the surrounding environment? Some scientists have speculated that these rings might eventually be absorbed into the galactic core, leading to the formation of a more centralized structure. Others suggest that they might persist for billions of years, contributing to the overall stability and appearance of their host galaxies. As we continue to discover more kiloparsec rings, particularly in distant galaxies, the diversity in their properties offers a tantalizing hint of the variety of galactic environments in the universe. While some rings are closely aligned with their galaxy's spiral arms, others may be found in irregular galaxies or elliptical galaxies, further complicating our understanding of how these rings form and evolve. This diversity in kiloparsec rings could suggest that there are multiple pathways for their creation, influenced by factors such as galaxy type, gas distribution, and external forces. By cataloging these various forms, astronomers can begin to piece together a more comprehensive picture of how these cosmic features fit into the larger framework of galaxy formation and evolution. While much has been discovered about kiloparsec rings, many questions remain unanswered. Are they a feature unique to certain types of galaxies, or do they occur more frequently than previously thought? How do they interact with the broader galactic environment, particularly in terms of the cosmic gas and dark matter that permeate space? And crucially, can the study of kiloparsec rings offer a deeper understanding of the forces at play in the very early stages of galaxy formation? These questions continue to challenge scientists, but each new discovery brings us closer to unlocking the secrets of these cosmic rings. One particularly fascinating aspect of kiloparsec rings is their potential to tell us about the state of the universe during earlier epochs. By studying these rings in distant galaxies, we may gain insights into the conditions that prevailed in the early universe, helping us understand how galaxies formed and evolved over time. Since many kiloparsec rings are located in galaxies billions of light-years away, they allow us to peer back in time, offering a glimpse into the distant past. In this sense, studying kiloparsec rings is not just about understanding the present state of galaxies, but also about tracing the history of cosmic structures from their infancy to their current form. The importance of the upcoming technological advancements, such as the James Webb Space Telescope and other advanced observatories, cannot be overstated in this context. These new instruments will provide an unprecedented ability to examine distant galaxies and their kiloparsec rings in incredible detail, allowing for the detection of faint signals and complex interactions that were previously beyond our reach. By observing the early stages of star formation in these distant rings, scientists may uncover crucial information about how galaxies assembled their stars and gas over time. Additionally, the study of these distant rings will reveal more about the different conditions under which kiloparsec rings form, perhaps even shedding light on entirely new processes that were previously undetected. The concept of star formation in kiloparsec rings offers a fresh perspective on galactic evolution. When we think about star formation, we often picture isolated regions of space, such as nebulae, where new stars are born from dense clouds of gas. However, kiloparsec rings defy this conventional understanding by representing enormous, galaxy-wide regions where star formation occurs simultaneously on a massive scale. This widespread activity may lead to the formation of entire generations of stars in a relatively short amount of time compared to other regions of galaxies. The large scale of star formation in these rings could provide a more efficient means of converting gas into stars, a process that could ultimately influence the galactic population over long periods. In the future, studying kiloparsec rings may also help scientists to uncover how the galactic environment affects the formation of different types of stars. The presence of intense star formation in these rings suggests that the physical conditions, such as temperature, pressure, and gas density, are ideal for the birth of new stars. However, these conditions can vary dramatically depending on the specifics of the galaxy in question. For example, galaxies with active central regions or those in the process of a merger may exhibit different types of star formation than more stable, isolated galaxies. By comparing the characteristics of kiloparsec rings across various galaxies, scientists can better understand how star formation depends on the larger galactic environment. One of the key goals of ongoing research into kiloparsec rings is to uncover the true extent of their impact on the overall galactic structure. Do these rings act as the main driver of star formation in their host galaxies, or are they secondary features that are eventually subsumed by the larger dynamics of the galaxy? Understanding this relationship could offer crucial insights into how different regions of a galaxy interact with each other, both in terms of star formation and overall galactic evolution. The degree to which kiloparsec rings influence their host galaxies could shed light on whether these rings are transient features that disappear over time, or whether they play a long-term role in shaping the structure of the galaxy. As scientists continue to study kiloparsec rings, one of the most intriguing aspects is their role in the overall stability and longevity of their host galaxies. Could these rings play a crucial part in regulating the galaxy's star formation process over time? Some researchers believe that kiloparsec rings might act as stabilizing mechanisms, helping to maintain the balance between gas, dust, and newly formed stars. Their vast size and immense scale could serve to distribute material more evenly across the galaxy, preventing overconcentration in certain regions and ensuring that star formation occurs in a more uniform manner. This type of regulation could be essential for maintaining the overall health of a galaxy, particularly as it matures and undergoes various transformations. Moreover, kiloparsec rings may provide valuable insights into the effects of galactic interactions, particularly in terms of galaxy mergers and interactions with other cosmic structures. Galaxy collisions are known to trigger bursts of star formation, but what happens when two galaxies with kiloparsec rings collide? Does this result in an even more intense star-forming region, or do the rings dissipate and reconfigure into new structures? The merging of galaxies with these giant rings could offer a fascinating natural laboratory for studying the most extreme types of galactic evolution, potentially leading to the creation of entirely new types of galaxies that may not exist in isolation. Looking beyond the rings themselves, studying the gas and dust surrounding them can also provide essential clues about the processes driving star formation in these galactic regions. These structures contain vast amounts of cold gas, much of which is dense enough to collapse under its own gravity, eventually leading to the formation of stars. However, the complex interplay between gas pressure, magnetic fields, and rotational motion could significantly affect how star formation proceeds. Understanding the mechanisms that govern these processes could allow astronomers to develop more accurate models of how galaxies form and evolve. For instance, could gas in a kiloparsec ring be funneled into the center of the galaxy over time, creating a burst of star formation in the core, or does the ring serve as a stable reservoir that feeds new stars in a more gradual fashion? In addition to their role in star formation, kiloparsec rings may also hold the key to understanding the larger-scale structure of the universe. By examining how these rings fit into the broader context of galactic interactions, astronomers can gain insights into the distribution of matter across the cosmos. These rings are often found in galaxies that are interacting with their neighbors or undergoing major transformations, suggesting that they could play a significant role in the larger cosmic ecosystem. This broader perspective could help us understand how galaxies form, grow, and evolve over cosmic timescales. The investigation of kiloparsec rings is also closely tied to the study of galaxy morphology. Galaxies come in many different shapes and sizes, from the well-known spiral galaxies to the more enigmatic elliptical galaxies, and kiloparsec rings are often associated with certain types of galaxies. Understanding where and why these rings form could shed light on the underlying processes that determine the shape and structure of galaxies. Are kiloparsec rings more likely to form in spiral galaxies with abundant gas, Or do they occur in elliptical galaxies as well? The answer could help astronomers refine their models of galaxy formation and provide new insights into how the different components of a galaxy, stars, gas, dust, and dark matter, interact to produce the complex structures we observe in the universe. As more advanced telescopes and observatories come online, the study of kiloparsec rings is expected to enter a new phase of discovery. Instruments such as the James Webb Space Telescope will allow astronomers to peer deeper into space than ever before, revealing more distant galaxies and their hidden rings. These discoveries will open new doors for understanding the formation and evolution of galaxies, as well as the role that star formation plays in these processes. The use of high-resolution imaging and spectroscopy will provide a wealth of data, allowing scientists to map the gas, dust, and stars in kiloparsec rings with unprecedented precision. In the coming decades, scientists are likely to continue uncovering new features of kiloparsec rings, revealing their importance in the broader context of galaxy formation and evolution. Some rings may be found to harbor unique types of star-forming activity, possibly revealing entirely new kinds of stellar populations or galactic processes. The discovery of more kiloparsec rings, particularly in distant galaxies, will expand our understanding of the cosmic landscape and allow us to trace the history of star formation across the universe. As we continue to investigate these mysterious cosmic structures, we may uncover even deeper layers of the universe's history, offering a glimpse into the fundamental processes that shape the galaxies we see today. Kiloparsec rings are much more than just fascinating features of galaxies. They represent a significant aspect of galactic dynamics and evolution. From their role in triggering star formation to their potential connections with supermassive black holes, kiloparsec rings offer an extraordinary window into the complexities of the cosmos. As scientists continue to explore these enigmatic rings, we are sure to uncover new insights into the fundamental processes that govern the formation and evolution of galaxies. The study of kiloparsec rings is not only a journey into the heart of individual galaxies, but also an exploration of the larger forces shaping the universe itself. As our understanding of kiloparsec rings expands, it's also worth considering the connection between these rings and the broader cosmic structures they inhabit. Galactic rings, including those spanning kiloparsecs, often form in response to large-scale cosmic forces, such as interactions with other galaxies or the gravitational influence of nearby clusters. This process links the existence of these rings to the grander dynamics of the universe, helping to unravel how galaxies grow and evolve over billions of years. One crucial piece of the puzzle involves the observation of how kiloparsec rings interact with their surroundings, particularly in the context of galaxy clusters. Galaxies and clusters experience complex gravitational interactions, which can distort their shapes and trigger dramatic changes in their structure. In this environment, kiloparsec rings can act as indicators of these interactions, revealing important information about the history of the galaxy's interactions with its neighbors. A ring in a galaxy might be a relic of a past collision or a sign of an ongoing gravitational encounter. By studying how these rings form and evolve in clusters, scientists can gain valuable insights into the long-term fate of galaxies. The formation of kiloparsec rings in isolated galaxies, on the other hand, presents a different set of mysteries. Why do these rings form in some galaxies but not others, especially when the underlying conditions seem similar? Are there specific triggers, such as the presence of certain types of gas or the configuration of the galaxy's spiral arms, that make kiloparsec rings more likely to form? Understanding this phenomenon could lead to new breakthroughs in galaxy formation theory, shedding light on the detailed conditions required for the creation of these massive, star-forming structures. On a larger scale, studying kiloparsec rings can also inform our understanding of galactic feedback mechanisms. Galaxies are dynamic systems, constantly exchanging energy and material with their surroundings. As stars form in the dense gas within these rings, they produce powerful winds and radiation that can affect the surrounding interstellar medium. The energy released by young, massive stars can drive gas out of the rings, enriching the surrounding galaxy with new material. This process, known as feedback, plays a vital role in regulating star formation and the growth of galaxies. Kiloparsec rings, with their intense star-forming activity, may act as powerful engines of this feedback, redistributing matter and energy across the galaxy. In this way, they might help explain how galaxies evolve over cosmic time. Moreover, kiloparsec rings could provide essential clues about the interplay between dark matter and visible matter. Dark matter, the mysterious substance that makes up a significant portion of a galaxy's mass, has an indirect yet profound influence on galaxy formation. While dark matter does not emit light and is therefore invisible to telescopes, its gravitational pull can shape the behavior of stars, gas, and other matter in galaxies. The distribution of dark matter in and around kiloparsec rings might provide valuable data on how dark matter interacts with the rest of the galaxy. This could have far-reaching implications for our understanding of both galaxy formation and the elusive nature of dark matter itself. The detection and analysis of kiloparsec rings in distant galaxies are becoming increasingly possible due to advancements in astronomical technology. With the help of next-generation observatories, scientists are now able to probe the farthest reaches of the universe and detect faint, distant rings that were once beyond reach. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the upcoming James Webb Space Telescope are poised to revolutionize our understanding of these cosmic features. The ability to study kiloparsec rings in galaxies located billions of light-years away could offer insights into the conditions of the early universe and how star formation has evolved over time. Looking forward, it's possible that kiloparsec rings may reveal unexpected connections to other cosmic phenomena. For example, could there be a link between kiloparsec rings and the mysterious gamma-ray bursts or the formation of supermassive black holes? The energy released in these regions could potentially influence the surrounding galaxy in profound ways. Furthermore, there might be a relationship between kiloparsec rings and the formation of certain types of quasars, supermassive black holes at the centers of galaxies that emit enormous amounts of energy. If these connections can be established, it would dramatically alter our understanding of galactic evolution and the role of rings in the cosmos. The study of kiloparsec rings also holds promise for deepening our understanding of the nature of galaxies themselves. In particular, investigating how these rings evolve over time could offer a glimpse into the future of our own galaxy, the Milky Way. Although the Milky Way does not currently host a prominent kiloparsec ring, it is possible that such a structure could emerge in the future as the galaxy undergoes significant changes. By studying other galaxies with kiloparsec rings, we may be able to anticipate what might happen to our galaxy in the distant future. For now, the study of kiloparsec rings remains one of the most exciting and dynamic fields in modern astrophysics. These giant cosmic rings continue to reveal their secrets, offering insights into the processes that drive star formation, galactic evolution, and the distribution of matter across the universe. As new technologies and observational techniques are developed, scientists will continue to push the boundaries of our knowledge, unlocking the mysteries of these extraordinary structures. Each new discovery brings us one step closer to understanding the intricate and awe-inspiring mechanisms that shape the galaxies we see in the sky. Kiloparsec rings are not just fascinating cosmic structures but essential components of the broader galactic ecosystem. They serve as a bridge between star formation and the intricate gravitational dynamics that govern the universe. As our understanding of these structures deepens, so too will our knowledge of the universe's past, present, and future. With each new discovery, we move closer to unraveling the cosmic mysteries that lie at the heart of galaxies and the universe as a whole. As our exploration of kiloparsec rings progresses, it's worth considering the broader implications of these structures in relation to the overall life cycle of galaxies. The process of star formation within these rings is far from straightforward, often influenced by a wide variety of factors, from the interplay of gas and dust to the complex forces exerted by dark matter and supermassive black holes at galactic centers. The rings themselves provide a unique lens through which we can observe and understand these influences, offering valuable insights into how galaxies evolve over time. One of the most striking aspects of kiloparsec rings is the way they serve as a laboratory for the study of galactic dynamics. As we've seen, these rings are often the product of specific interactions or conditions within their galaxies. Whether caused by past galaxy collisions, internal structural rearrangements, or external gravitational disturbances, these rings tell a story of how galaxies adjust to their ever-changing environments. By studying the properties of these rings, such as their size, shape, and the rate of star formation within them, scientists can uncover crucial details about the forces that govern the structure and behavior of galaxies. For instance, the morphology of a kiloparsec ring, its size, symmetry, and the pattern of star formation within it, can provide important clues about the initial conditions that led to its formation. In some galaxies, these rings are the result of gravitational instabilities, while in others, they may have formed through the interaction of spiral arms with the central galactic disk. Understanding these processes in detail can shed light on how galaxies evolve over time and the role of external and internal forces in shaping their structure. In this context, it's essential to consider the role of galactic feedback mechanisms, which are often intricately tied to the formation and evolution of kiloparsec rings. Feedback, driven by star formation and the energy produced by young stars, has a profound impact on the surrounding environment, influencing gas dynamics and even the formation of new stars. Within kiloparsec rings, this feedback can be especially intense, as the rings often serve as regions of high star formation. The energy released by these stars can drive gas out of the rings and affect the galaxy's overall star formation rate. Moreover, the formation of kiloparsec rings may be intricately connected to the role of supermassive black holes at the centers of galaxies. These black holes, which can be millions to billions of times the mass of the Sun, exert a powerful gravitational influence on their surroundings. Their interactions with the gas and dust in a galaxy can trigger massive outflows, and in some cases, these outflows might even shape the formation of the rings themselves. This interplay between the black hole, the surrounding gas, and the star-forming regions of the kiloparsec rings is still not fully understood, but it's an area of intense research that could reveal new insights into the mechanics of galaxy evolution. Another intriguing aspect of kiloparsec rings is their potential connection to the broader process of galaxy formation in the early universe. Many of the galaxies that we observe today are remnants of ancient, primordial galaxies that formed billions of years ago. In the distant past, conditions in the universe were different, and the process of galaxy formation was driven by a combination of factors, including the availability of gas, the presence of dark matter, and the influence of cosmic radiation. It is possible that kiloparsec rings were more common in these early galaxies, acting as sites of intense star formation in an environment that was still in the process of settling into the stable configurations we see today. As we look further into the future, it's possible that kiloparsec rings may play a crucial role in the ultimate fate of galaxies. While the mechanisms that govern galaxy evolution are still not fully understood, one theory suggests that galaxies will eventually stop forming stars, entering a red and dead phase as their gas supply is exhausted. In this context, it's intriguing to consider how kiloparsec rings, with their high rate of star formation, might be one of the last bastions of activity in a dying galaxy. They could serve as the final remnants of a once thriving star-forming environment, lingering long after the rest of the galaxy has ceased to produce new stars. In addition to their role in galactic evolution, kiloparsec rings may also provide valuable information about the broader structure of the universe. The distribution of galaxies with kiloparsec rings, their locations within galaxy clusters, and their relationship to other cosmic phenomena can offer insights into the large-scale structure of the universe. This information can help astronomers understand the fundamental processes that drive the growth and evolution of cosmic structures over vast periods of time. As we continue to explore these fascinating structures, the advent of new observational techniques promises to revolutionize our understanding of kiloparsec rings. Instruments such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope will allow scientists to peer deeper into the universe, observing distant galaxies in unprecedented detail. These observations will provide crucial data on the physical conditions within kiloparsec rings, allowing scientists to better understand the factors that influence their formation and evolution. In the coming decades, it's likely that kiloparsec rings will continue to be a key focus of research in astrophysics. As our technology improves and our understanding of galaxy formation deepens, we will gain new insights into the complex processes that govern the universe. The study of these rings, with their intense star formation and intricate dynamics, will remain a critical area of investigation, shedding light on some of the most profound questions in modern astronomy. Ultimately, kiloparsec rings represent one of the many mysterious and awe-inspiring features of the universe, offering a glimpse into the dynamic processes that shape the galaxies we observe today. These giant rings of star formation, nestled in the heart of galaxies, provide a unique window into the forces that govern the evolution of galaxies over time. As we continue to study and explore these cosmic structures, we will undoubtedly uncover new and surprising insights into the universe's most fundamental workings. As we dive even deeper into the study of kiloparsec rings, it's important to consider how these cosmic features relate to other fascinating phenomena within galaxies. They aren't just isolated anomalies. They are intricately connected to the broader dynamics of galaxies and even the evolution of the universe itself. These rings, with their dense regions of star formation, can help to illuminate a host of cosmic processes, shedding light on the forces that have shaped, and will continue to shape, the galaxies we see around us. One of the key elements that makes kiloparsec rings so intriguing is their close association with the structural features of galaxies, particularly spiral galaxies. Spiral galaxies are known for their well-defined spiral arms, which are regions of intense star formation and stellar activity. But in many cases, these spiral arms are accompanied by a larger, more diffuse structure, the kiloparsec ring. These rings act as a kind of anchor for the spiral arms, guiding the flow of gas and helping to direct star formation in specific patterns. This relationship between spiral arms and kiloparsec rings highlights the interconnectedness of different features within galaxies, showing how complex and finely tuned the processes of galactic formation and evolution can be. In some galaxies, the presence of kiloparsec rings may be the result of external forces, such as interactions with neighboring galaxies. Collisions and gravitational interactions between galaxies are thought to be responsible for triggering the formation of many different kinds of galactic structures, and kiloparsec rings are no exception. When two galaxies collide, the immense gravitational forces at play can cause significant disturbances in the gas and dust within the galaxies. These disturbances can trigger waves of star formation, which may give rise to the formation of rings, sometimes with dramatic effects. The structure of the rings can be altered by the specific nature of the collision, whether it's a direct head-on collision or a more gentle grazing interaction, and these variations offer insights into the diverse ways in which galaxies can evolve in response to external forces. Interestingly, these rings are not confined to just one type of galaxy. Although they are most commonly found in spiral galaxies, they have also been observed in elliptical galaxies and irregular galaxies, though they appear in different forms and with varying characteristics. In elliptical galaxies, for example, kiloparsec rings tend to be more centrally concentrated, with star formation occurring in the outer regions of the galaxy's core. In irregular galaxies, the formation of rings can sometimes be more erratic, resulting in structures that are less symmetrical and more spread out across the galaxy. These differences provide valuable clues about the conditions and processes that govern the formation of kiloparsec rings and reveal how diverse the evolution of galaxies can be, even among similar types of galaxies. Beyond the structural implications, kiloparsec rings also hold the potential to reveal deeper truths about the universe itself. When we observe a kiloparsec ring, we are not only witnessing the process of star formation on a massive scale, we are also looking at the impact of cosmic forces such as dark matter, black holes, and even the larger-scale structure of the universe. Dark matter, for instance, plays a crucial role in the formation and stability of galaxies, and its presence may influence the behavior of kiloparsec rings. Since dark matter doesn't emit light and can't be directly observed, astronomers must infer its existence and properties by studying its gravitational effects on visible matter. Understanding how dark matter interacts with the gas and stars within a galaxy's kiloparsec ring could provide vital insights into its role in galaxy formation and evolution. Similarly, the role of supermassive black holes in the center of galaxies cannot be understated. These black holes are often found at the heart of the galaxy, and their immense gravitational pull can have far-reaching effects on the surrounding gas and stars. In some cases, the presence of a supermassive black hole may help to regulate the star formation within a kiloparsec ring, either by driving powerful outflows of gas or by preventing the collapse of material needed to form new stars. The exact relationship between kiloparsec rings and supermassive black holes is still an area of active research, but what is clear is that these cosmic giants are likely key players in the ongoing evolution of these extraordinary structures. The study of kiloparsec rings also intersects with the investigation of the broader dynamics of star formation. As we've seen, these rings are often characterized by intense bursts of star formation, fueled by the accumulation of gas and dust in specific regions of the galaxy. This star formation process is governed by a variety of factors, including the rate at which gas is funneled into the ring, the stability of the gas, and the presence of other cosmic forces, such as magnetic fields. By studying the rates of star formation within kiloparsec rings, astronomers can gain a deeper understanding of how stars are born and how galaxies evolve as a result of this continuous cycle of birth and death. One of the most important aspects of star formation in kiloparsec rings is the role of gas. The rings themselves are often made up of a vast reservoir of molecular gas, which provides the raw material needed to create new stars. However, this gas is not always evenly distributed, and in some cases, the gas can be channeled into specific regions of the ring, where it undergoes compression and heating, leading to the formation of stars. The rate at which this star formation occurs depends on a number of factors, including the temperature and density of the gas, as well as the presence of other elements that can trigger or inhibit the process. By studying the distribution of gas within kiloparsec rings, astronomers can learn more about the conditions that foster star formation and how these conditions vary across different types of galaxies. As we continue to explore the mysteries of kiloparsec rings, it's clear that these cosmic structures are far more than just regions of intense star formation. They are windows into the intricate processes that govern the evolution of galaxies and the universe as a whole. Through the study of these rings, we can learn more about the forces that shape galaxies, the role of dark matter and black holes in galactic evolution, and the fundamental processes that govern the birth and death of stars. Kiloparsec rings, in all their complexity and mystery, offer us a deeper understanding of the cosmos and the ongoing story of the universe's evolution. In the future, the continued advancement of astronomical techniques and technologies promises to unlock even more secrets about these fascinating structures. Instruments such as the James Webb Space Telescope, which is capable of observing galaxies in unprecedented detail, will allow scientists to peer even further into the universe, offering new insights into the formation and evolution of kiloparsec rings. With each new discovery, we move closer to understanding the full scope of these cosmic structures and their role in the grand cosmic tapestry. For now, however, kiloparsec rings remain a fascinating enigma, their intricate star formation processes and complex dynamics continuing to intrigue astronomers and cosmic enthusiasts alike. As our understanding of these structures deepens, one thing is certain: the more we learn about kiloparsec rings, the more we uncover about the vast and ever-changing universe that surrounds us. These rings, in all their cosmic glory, serve as a reminder of the beauty and complexity of the universe, a universe that continues to surprise and inspire us, no matter how much we think we know. As we venture deeper into the study of kiloparsec rings, it's essential to look at how these structures contribute to our understanding of the life cycle of galaxies. In essence, kiloparsec rings are not just passive features. They are active participants in the cosmic dance of birth, death, and rebirth within galaxies. This interplay between the formation of stars, the accumulation of gas, and the complex forces that shape these rings offers astronomers valuable insight into the mechanisms that drive galactic evolution on a grand scale. The process of star formation within kiloparsec rings is often cyclical. Gas clouds within these rings can condense under the right conditions, forming new stars that, over time, will eventually burn out and die. This stellar cycle not only transforms the structure of the ring itself, but also has broader implications for the overall dynamics of the galaxy. As stars are born and evolve, they release energy and material into the surrounding space, enriching the galaxy with elements created in their cores. This process of stellar feedback is a critical component in the ongoing evolution of galaxies, as it influences the rates of star formation, the dynamics of gas clouds, and even the gravitational interactions that govern the movement of stars and other objects within the galaxy. In some cases, the birth and death of stars within kiloparsec rings can lead to dramatic changes in the structure of the galaxy itself. For instance, the formation of massive stars or even supernovae can inject enormous amounts of energy into the surrounding gas, pushing it outward and causing ripples throughout the galaxy. These ripples can, in turn, alter the dynamics of the galaxy, affecting everything from the motion of stars to the formation of new structures. These changes are not always predictable, and in some instances, they may lead to the creation of entirely new rings or the disruption of existing ones. This feedback loop between star formation, stellar death, and the evolution of the galaxy's structure is one of the key reasons why kiloparsec rings are so intriguing. They offer a glimpse into the dynamic processes that govern the life and death of galaxies. Furthermore, the study of kiloparsec rings can shed light on the processes that shape the larger-scale structure of the universe. When we observe a kiloparsec ring, we're not just seeing a localized event occurring within a single galaxy. We're witnessing the product of broader cosmic forces at play. Gravitational interactions between galaxies, the influence of dark matter, and the effects of supermassive black holes all play a role in shaping the evolution of these cosmic structures. As we gather more data and refine our understanding of these interactions, we begin to realize that kiloparsec rings are not just isolated features. They are part of a much larger and more complex web of cosmic phenomena that stretches across the universe. One of the more fascinating aspects of kiloparsec rings is their potential to act as laboratories for studying the fundamental forces that govern the universe. These rings are essentially natural experiments in the field of astrophysics, offering astronomers a unique opportunity to observe the interplay of gas, stars, and dark matter on a grand scale. By studying the formation and evolution of kiloparsec rings, we can learn more about the fundamental processes that drive the creation of galaxies, stars, and other cosmic structures. In this sense, kiloparsec rings are not just curiosities. They are key pieces of the cosmic puzzle, offering critical insights into the mechanics of the universe. In addition to their role in galactic evolution, kiloparsec rings can also provide important clues about the origins of galaxies themselves. Understanding how these rings form, evolve, and interact with their surroundings can offer valuable insights into the conditions that gave rise to the first galaxies in the universe. Some of the earliest galaxies likely formed in a similar manner to the way kiloparsec rings emerge, with gas being funneled into specific regions where intense star formation occurred. By studying the properties of these rings, astronomers can gain a better understanding of how galaxies formed and evolved in the early universe, providing important clues about the conditions that led to the birth of the galaxies we see today. Moreover, the study of kiloparsec rings intersects with another fascinating area of research, the search for extraterrestrial life. While these rings themselves may not be directly related to the search for life, the processes that occur within them, particularly the formation of new stars and planets, may play a role in the creation of environments where life could potentially arise. As new stars are born within these rings, they may give rise to planets in the habitable zone, regions where liquid water could exist and where life, as we understand it, could thrive. In this way, the study of kiloparsec rings indirectly contributes to our quest to understand the conditions necessary for life to exist elsewhere in the universe. The role of kiloparsec rings in shaping planetary systems also warrants further exploration. As the stars within these rings evolve and create heavy elements through nuclear fusion, they enrich the surrounding gas clouds, creating a fertile environment for the formation of planets. Some of these planets may end up in the habitable zone of their respective stars, where conditions are right for the emergence of life. As astronomers continue to study the chemical composition of the gas and dust in these rings, they may uncover new insights into the types of materials that could lead to the formation of life-supporting planets. This exploration of the relationship between star formation and planetary formation in kiloparsec rings adds another layer of complexity to our understanding of how life may exist elsewhere in the universe. As technology continues to advance, the tools available to study kiloparsec rings are improving at an exponential rate. Instruments like the James Webb Space Telescope, which is designed to observe distant galaxies with unprecedented detail, are opening up new frontiers in our understanding of cosmic structures like kiloparsec rings. The ability to observe these rings in multiple wavelengths, from infrared to X-ray, will provide scientists with an unprecedented view of the physical processes taking place within these structures. This new data will undoubtedly lead to new discoveries about the role of kiloparsec rings in galaxy formation, star formation, and the evolution of the universe. Moreover, the development of more powerful supercomputers will allow astronomers to simulate the complex dynamics of kiloparsec rings with greater accuracy. These simulations will provide valuable insights into the physical processes that govern the formation and evolution of these rings, including the effects of gravity, gas dynamics, and star formation. By combining observational data with computational models, scientists will be able to refine their understanding of how kiloparsec rings come into being and how they evolve over time. This combination of observational and computational techniques holds the key to unlocking many of the remaining mysteries surrounding these cosmic structures. Despite all the progress that has been made, there is still much to learn about kiloparsec rings. These structures remain one of the most fascinating and enigmatic features in the universe, and their study continues to push the boundaries of our understanding of astrophysics. As we continue to observe these rings with more advanced tools and techniques, we are bound to uncover even more mysteries that will continue to challenge our perceptions of the universe and deepen our appreciation for the complexity and beauty of the cosmos. The study of kiloparsec rings is a reminder of how much we still have to discover about the universe. These cosmic structures, with their intricate patterns of star formation and their connections to the larger-scale dynamics of galaxies, offer a glimpse into the profound processes that govern the evolution of the cosmos. As we continue to explore these rings and the forces that shape them, we move closer to understanding the grand story of the universe, one that is still unfolding, and one that will continue to surprise and fascinate us for generations to come. As we continue to delve into the mysteries of kiloparsec rings, it's important to acknowledge how they stretch our understanding of galactic structures. These structures, often seen as rings of intense star formation, challenge the conventional wisdom about how galaxies evolve. Rather than being simply passive relics or side effects of galactic processes, kiloparsec rings reveal themselves to be dynamic and evolving features that can provide critical insights into the physical and chemical evolution of galaxies. One of the most compelling aspects of kiloparsec rings is their ability to form in galaxies with different types of structures and histories. Whether a galaxy is a barred spiral, an elliptical, or even an irregular shape, kiloparsec rings can emerge in a variety of galactic environments. This diversity in galactic types suggests that the mechanisms responsible for the formation of these rings may be more universal than we initially thought. They may be driven by interactions with other galaxies, the presence of a central supermassive black hole, or even the sheer gravitational dynamics of the galaxy itself. Studying the wide variety of galaxies in which kiloparsec rings form can help us piece together the different ways these cosmic structures can evolve and the conditions that make their formation possible. Galactic interactions are often a major factor in the creation of kiloparsec rings. For example, collisions or near collisions between galaxies can redistribute gas and dust, funneling material into specific regions of a galaxy. This material can then undergo compression, triggering intense star formation and the creation of a kiloparsec ring. These galactic mergers and interactions not only give rise to spectacular visual phenomena but also allow astronomers to study the intricate mechanisms of galaxy formation and evolution in real time. The way in which a galaxy reacts to an interaction, such as the formation of a ring or the triggering of star formation, can provide insights into the dynamics of the galaxy itself, as well as the underlying forces at play within the broader cosmic landscape. As we observe more galaxies and their kiloparsec rings, it becomes increasingly clear that these rings are not simply the product of isolated events. They are, in fact, influenced by a combination of factors that extend far beyond the rings themselves. One such factor is the behavior of dark matter, the mysterious and invisible substance that makes up a significant portion of the mass in the universe. Dark matter's gravitational influence on galaxies can shape the dynamics of these galaxies in profound ways. By examining how dark matter interacts with gas clouds and stars in galaxies with kiloparsec rings, astronomers can gain a better understanding of how dark matter influences the formation and evolution of these rings. This connection between dark matter and kiloparsec rings opens up an exciting avenue of research, with the potential to reveal new insights into one of the greatest mysteries in astrophysics. In addition to dark matter, another intriguing component that plays a role in the formation of kiloparsec rings is the presence of a supermassive black hole at the center of many galaxies. These black holes exert immense gravitational forces on the surrounding material, and in some cases, this influence may contribute to the creation of rings of gas and stars around them. The presence of these black holes could act as a catalyst, triggering the collapse of gas clouds into new stars or pushing gas into specific regions where it condenses into a ring-like structure. The relationship between kiloparsec rings and supermassive black holes is an area of ongoing research, with many unanswered questions about how these black holes contribute to the formation and evolution of these cosmic rings. Interestingly, the study of kiloparsec rings is also shedding light on a broader question in astronomy: the nature of galaxy morphology. Historically, galaxies have been classified based on their shapes: spirals, ellipticals, and irregulars. However, the discovery of kiloparsec rings challenges this neat classification system. These rings can form in galaxies with a range of shapes and sizes, and their presence often indicates that the galaxy has undergone some form of significant interaction or transformation. In this sense, kiloparsec rings are blurring the lines between different types of galaxies, prompting astronomers to reconsider the way they classify and study these celestial objects. The interplay between the galactic environment, star formation, dark matter, and supermassive black holes within galaxies with kiloparsec rings is a prime example of the complexity that exists in the universe. Each galaxy is unique, shaped by its own history of interactions, collisions, and internal dynamics. Yet, despite this complexity, kiloparsec rings remain a constant feature in the landscape of galaxy evolution, offering astronomers a window into the ongoing processes of galaxy formation and transformation. By studying these rings in greater detail, we are not just learning about one particular type of galactic structure, we are gaining a deeper understanding of the forces that govern the formation of galaxies themselves. As new telescopes and instruments continue to push the boundaries of our observational capabilities, the study of kiloparsec rings is expected to yield even more exciting discoveries. For example, next-generation space observatories like the James Webb Space Telescope will allow scientists to observe these rings with greater resolution and sensitivity than ever before. This means that we may soon be able to study the very processes that govern the birth of stars in these rings, as well as the complex interplay of forces that shape them. The ability to observe kiloparsec rings in greater detail will undoubtedly lead to new breakthroughs in our understanding of galaxy formation, stellar evolution, and the larger-scale structure of the universe. Even beyond the realm of astronomy, the study of kiloparsec rings has broader implications for our understanding of the universe. These cosmic structures, with their intricate patterns of star formation and the rich tapestry of interactions that lead to their creation, highlight the interconnectedness of all things in the universe. From the formation of galaxies to the creation of stars and planets, everything is part of a vast and intricate web of cosmic processes that stretches across time and space. By studying kiloparsec rings, we are not only learning about the specific dynamics of a particular galaxy or region of the universe, we are gaining a deeper appreciation for the profound and awe-inspiring complexity of the cosmos as a whole. The mysteries surrounding kiloparsec rings are far from solved, and the field of study continues to evolve. With each new discovery, we are expanding our understanding of how galaxies form and evolve, and how the forces of nature interact on the grandest scales. As our knowledge of kiloparsec rings grows, so too does our appreciation for the beauty and intricacy of the universe. These cosmic rings, once thought to be mere curiosities, are now seen as key pieces in the puzzle of galactic evolution. They offer a glimpse into the past, present, and future of galaxies, and provide a window into the deep and profound processes that govern the cosmos. Kiloparsec rings are much more than just visually striking features in distant galaxies. They are active participants in the dynamic and ongoing process of galactic evolution. Through their formation, evolution, and interaction with other components of the galaxy, they offer valuable insights into the mechanisms that drive the creation of galaxies, stars, and other cosmic structures. By studying kiloparsec rings, astronomers are not only gaining a deeper understanding of the forces that shape our universe, but they are also uncovering the mysteries of the cosmos itself, one ring at a time. As we continue to examine the fascinating world of kiloparsec rings, it becomes clear that they are not merely a curiosity in the sky, but rather, essential structures for understanding how galaxies evolve. These rings, often far from the center of their host galaxies, display an intense activity of star formation that seems at odds with their placement in the galaxy's structure. The more we observe these cosmic structures, the more we realize they are key to unlocking the mysteries of stellar life cycles, galactic dynamics, and the hidden forces that shape the very fabric of our universe. A crucial aspect of kiloparsec rings is the varying mechanisms behind their formation. It was once believed that these rings could only form in certain types of galaxies. But as our observational tools have improved, we've discovered that they can emerge in an array of galactic environments. From the tidally triggered rings emerging galaxies to those resulting from resonances within the galactic disk, the circumstances that bring about these rings are diverse, offering a window into the many ways galaxies interact with each other and evolve over time. The role of galactic bars in the formation of kiloparsec rings is particularly noteworthy. Galactic bars, long thought to be simply structural features of certain spiral galaxies, are now understood to be instrumental in funneling gas into the central regions of galaxies. This influx of gas can lead to the formation of intense star-forming regions, which may manifest as kiloparsec rings. In fact, the star formation observed in these rings often occurs in a spiral-like pattern, reflecting the dynamic nature of the galactic bar itself. The bar's gravitational influence redistributes material, pushing it into the ring structure, and in some cases, this process results in a burst of star formation that lasts millions of years. This interplay between galactic bars and kiloparsec rings is a perfect example of how galaxy evolution is driven by a delicate balance of gravitational forces, gas dynamics, and stellar evolution. Another critical aspect of these cosmic rings is the complex relationship between star formation and the surrounding interstellar medium. The gas clouds within kiloparsec rings are often densely packed with dust and other elements, providing the raw material for new stars. However, it's not just the amount of gas that matters, it's the conditions in which it's found. The temperature, density, and pressure of the gas all play a role in determining whether it will collapse to form stars or remain diffuse. This delicate balance between the gas environment and star formation is key to understanding how these rings evolve over time. While some rings may be in a state of continuous star formation, others may show evidence of periods of quiescence or even starburst activity, where a large number of stars form in a short time. The chemical composition of kiloparsec rings is also a fascinating area of study. When we observe the light emitted from these rings, we can detect the spectral lines that tell us about the chemical elements present in the gas. This information can reveal the history of star formation in the ring and give us clues about the conditions that existed in the galaxy at different points in time. For instance, high levels of certain elements like oxygen and nitrogen can indicate regions where massive stars have formed and exploded as supernovae, enriching the surrounding medium with heavier elements. On the other hand, a lack of certain elements might suggest that star formation in the ring is relatively young, or that the ring is being influenced by the gas in the outer regions of the galaxy. The interaction between the stars in the ring and the galaxy's overall structure is another important facet of kiloparsec rings. As new stars form in the ring, they are not isolated entities. They interact with the existing stars and gas within the galaxy, influencing the dynamics of the entire system. These interactions can result in the movement of material within the ring, the formation of new structures, and even the gradual dissolution of the ring itself. The study of these interactions is a critical component in understanding the long-term fate of kiloparsec rings and how they contribute to the overall evolution of their host galaxies. Another intriguing aspect of kiloparsec rings is their potential link to galaxy evolution across cosmic time. By studying these structures in distant galaxies, we are essentially looking back in time, observing galaxies at different stages of their life cycles. The rings we see today may offer insights into the conditions of galaxies billions of years ago, when they were first forming or undergoing significant transformations. As galaxies collide and merge over cosmic time, they leave behind signatures in the form of kiloparsec rings. These rings, along with other features like tidal tails and distorted gas clouds, can serve as relics of past interactions, helping us trace the evolution of galaxies across the universe. Moreover, the study of kiloparsec rings in the context of galaxy clusters is another exciting frontier. In galaxy clusters, where hundreds or even thousands of galaxies are bound together by gravity, the interaction between galaxies is even more pronounced. These interactions can lead to the formation of rings in galaxies that would not have otherwise formed them in isolation. Studying kiloparsec rings in such environments could provide new insights into the role of large-scale cosmic structures in the evolution of individual galaxies. Furthermore, the high density of galaxies in clusters may offer a unique opportunity to observe the effects of repeated galactic mergers and interactions, providing a clearer picture of how these processes contribute to the formation of kiloparsec rings. The emerging field of computational astrophysics is also playing a significant role in our understanding of kiloparsec rings. With increasingly sophisticated simulations, scientists are able to model the intricate dynamics of galaxies and their components, including kiloparsec rings. These simulations take into account the complex interplay of gravitational forces, gas dynamics, and star formation, allowing researchers to explore different scenarios and predict how kiloparsec rings might form under various conditions. As computational power continues to grow, these simulations will become even more accurate, providing a detailed and comprehensive picture of the processes that drive the formation and evolution of these cosmic structures. Observations from future space telescopes like the James Webb Space Telescope and ground-based observatories will continue to advance our knowledge of kiloparsec rings. By studying these structures in greater detail, and over a wider range of wavelengths, scientists will be able to probe the physical conditions that lead to the formation of these rings and understand their role in the broader context of galactic evolution. The high-resolution imaging capabilities of these telescopes will allow us to observe the intricate details of kiloparsec rings, providing insights into the star formation processes, the chemical composition of the gas, and the dynamics of the surrounding galaxy. As our understanding of kiloparsec rings deepens, we are also learning more about the broader processes of galaxy evolution. These rings are not isolated phenomena but are part of the larger picture of how galaxies change over time. By studying kiloparsec rings, we can gain a better understanding of the forces that shape galaxies, from the gravitational interactions that drive their motion to the internal processes that govern star formation and chemical evolution. This knowledge is essential for piecing together the history of the universe and understanding how the galaxies we see today came to be. In conclusion, kiloparsec rings are not just remarkable features in the sky. They are vital tools for understanding the evolution of galaxies and the complex processes that shape the universe. From their formation in response to galactic interactions and the influence of dark matter and supermassive black holes, to their role in star formation and the chemical enrichment of galaxies, these rings offer a unique and fascinating window into the workings of the cosmos. As our observational tools and theoretical models continue to improve, the study of kiloparsec rings will no doubt yield even more groundbreaking discoveries, further illuminating the intricate and awe-inspiring nature of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.